Hello, and welcome. Tonight, we are going to do something a little different. We are going to take a very long, very slow journey into the hidden world of lava chemistry. And if that sounds complicated or demanding, please let go of that thought right now. There is nothing you need to remember. There is nothing you need to study. You are simply here to rest. And if a few fascinating ideas drift through your mind along the way, that is a lovely bonus, but it is not required. So settle in. Find a comfortable position. Let your body feel heavy against whatever surface is holding you. Let your breathing be easy and natural. There is no rush tonight. We have hours ahead of us, and every single one of them belongs to you. Somewhere deep beneath the ground you are lying on right now, far below the soil and the stone and the layers of ancient sediment, the earth is warm. Not just warm, really, but genuinely hot. Hot enough that rock, the very substance we think of as the most solid, most permanent thing in our world, becomes something else entirely. It softens, it loosens, it begins to flow. And when that flowing rock eventually finds its way to the surface, we call it lava. That is the simplest version of what we are going to talk about tonight. Lava, molten rock, glowing, slow, ancient, and full of chemistry that most people never think about. But we are going to think about it gently, like watching clouds from a hammock. We will let the ideas come and go. Some will linger, some will pass, and that is perfectly fine. If you fall asleep in the next few minutes, wonderful. If you stay awake for the whole journey, also wonderful. There is no wrong way to listen to this. The lava will keep flowing, whether you are awake or asleep, and the chemistry will still be there in the morning, quietly shaping the world beneath your feet. For now, just breathe. Let your eyes close if they have not already, and imagine, if you like, a landscape at dusk. The sky is deep amber and violet. The air is warm but still. And somewhere in the distance, very far away, there is a faint orange glow near the horizon. That glow is lava, and it has been there for a very, very long time. We are going to start simply. We are going to talk about what lava actually is in the most gentle and straightforward way. And then, slowly, over the course of the next few hours, we will go deeper. We will look at the atoms and the minerals. We will talk about the elements that make up molten rock. We will explore how different types of lava behave and why some flows are smooth and others are rough. We will peek into the microscopic world inside a drop of lava where crystals are forming like tiny lanterns in a glowing sea. And later, much later, we will drift beyond Earth entirely and visit the lava of other worlds, the ancient basalt plains of the Moon, the volcanic landscapes of Mars, the extraordinary eruptions on a tiny moon called Io, far out in the orbit of Jupiter. But all of that is ahead of us. For now, there is nothing you need to do but rest. Let us begin with the basics, spoken softly, as if we were sitting together by a quiet fire. Lava is molten rock that has reached the surface of the earth. That is the key distinction. When that same molten material is still underground, still moving through channels and chambers deep inside the planet, we call it magma. The substance is essentially the same, but the name changes depending on where it is. Magma is below. Lava is above. It is a simple difference, but a useful one. You might picture magma as a hidden river, flowing very slowly through vast underground reservoirs. These reservoirs are called magma chambers, and they can sit many miles below the surface, tucked into the lower crust or even near the boundary between the crust and the mantle. The mantle is the thick, hot layer of the earth that lies between the thin outer crust and the deep, dense core. Most of Earth's interior is mantle, and it is from the mantle that nearly all magma originally comes. Now, magma is not simply a pure liquid. It is a complex mixture. Imagine a very thick, very hot soup made of melted minerals, with tiny crystals floating in it, and dissolved gases bubbling through it. The liquid part is called the melt, and it is made mostly of silicate compounds, which we will talk about more in a little while. The crystals are minerals that have already begun to solidify, even though the rest of the mixture is still molten. And the gases, well, they are mostly water vapor, carbon dioxide, and sulfur dioxide, trapped under enormous pressure. When magma rises toward the surface, it does so because it is lighter than the solid rock around it. Think of it as buoyancy, the same principle that makes a bubble rise in water. The molten rock is less dense than the surrounding stone, and so it drifts upward very slowly through cracks and weaknesses in the crust. This journey can take thousands of years, or sometimes it can happen much more quickly, depending on the conditions. And when the magma finally reaches the surface, when it spills out onto the ground or flows into the sea, it becomes lava. The pressure drops. The dissolved gases begin to escape, like the fizz leaving a bottle of sparkling water when you open the cap. The temperature is still extraordinary, often between 700 and 1200 degrees Celsius. But now the lava is exposed to the air, or to ocean water, and it begins to cool. This cooling is one of the most important things that happens to lava, and we will come back to it many times tonight, because it is in the cooling that the chemistry of lava becomes visible. The minerals crystallize, the textures form, the rock takes shape, but all of that unfolds slowly, and there is no need to hurry toward it. Let us stay here for a moment. In this simple picture, magma below, lava above, a hot, glowing mixture of melt, crystals, and gas, rising gently through the earth. If you imagine the earth as a very large, very old fruit, the crust is the thin skin, the mantle is the thick flesh beneath, and the magma is like a slow, warm syrup moving through the deeper layers, occasionally finding a path to the surface. It is a peaceful image, and it is not so far from the truth, at least in spirit. The timescales involved are immense. The magma that feeds a particular volcanic region may have begun its journey millions of years ago. It rises, pauses, cools slightly, melts again, mixes with other batches of magma, and continues its slow ascent. By the time it reaches the surface as lava, it carries within it a chemical record of everything it has encountered along the way. Every mineral it dissolved, every gas it absorbed, every crystal it grew and then remelted. Lava is, in a sense, a diary of the deep earth, written in chemistry. And that diary is what we are going to read together tonight, not with urgency or demand, but with the quiet curiosity of someone leafing through an old, beautiful book by lamplight. There is so much to discover, and we have all the time in the world. Now, let us gently turn our attention to the chemistry itself. And please, if the word chemistry makes you feel tense or reminds you of difficult exams, let that feeling go. The chemistry of lava is not something you need to memorize or master. It is something you can simply appreciate, the way you might appreciate the colors in a sunset without needing to know the physics of light scattering. The most important ingredient in lava, by far, is something called silica. Silica is a compound made of two of the most common elements on Earth, silicon and oxygen. Together, silicon and oxygen form the backbone of almost every mineral in the Earth's crust. They link together in tiny structures called silicate tetrahedra, which you can think of as miniature pyramids, each one made of one silicon atom surrounded by 4 oxygen atoms. These little pyramids are everywhere in geology. They are the building blocks of quartz, of feldspar, of mica, of olivine, of so many minerals that make up the rocks beneath your feet. And in lava, these silicate tetrahedra are the dominant players. They float and drift and connect to each other in the molten liquid, forming chains and sheets and networks that give the lava its texture and its behavior. The amount of silica in a particular batch of lava determines almost everything about how that lava will behave. This is one of the most important ideas in all of volcanology, and it is a beautifully simple one. More silica means thicker, stickier lava. Less silica means thinner, runnier lava. That is the core principle, and it applies across almost every volcanic system on Earth. Geologists have a way of classifying lavas based on their silica content. At the low end, with about 45 to 52% silica, we have what are called mafic lavas. The word mafic comes from magnesium and ferric, which is another way of saying iron. These lavas are rich in magnesium and iron, and they tend to be dark in color, very hot, and very fluid. They flow easily, like a slow, sleepy river of glowing orange rock. Basalt is the most common rock that forms from mafic lava, and basalt is the most common volcanic rock on Earth. It makes up the ocean floors. It covers vast plains in places like Iceland and Hawaii. It is a quiet, dependable kind of rock, dark and dense and ancient. At the other end of the spectrum, with about 63% silica or more, we have felsic lavas. The word felsic comes from feldspar and silica, two of its dominant components. Felsic lavas are lighter in color, cooler in temperature, and much thicker and stickier than mafic lavas. They move reluctantly, like cold honey, or like thick batter being poured very slowly from a bowl. When felsic lava cools, it forms lighter colored rocks like rhyolite and dacite, and in between mafic and felsic, there are intermediate lavas with silica content somewhere in the middle. Andesite is a common intermediate rock, named after the Andes Mountains, where this kind of volcanism is particularly common. Intermediate lavas behave in ways that are, as you might expect, somewhere between the two extremes. Not as runny as basalt, not as sticky as rhyolite, just somewhere in the gentle middle. You can think of it like this. Imagine 3 different liquids being poured. The mafic lava is like warm olive oil, flowing easily across a surface, spreading out thin and wide. The intermediate lava is like thick syrup, moving more slowly, building up a bit before spreading. And the felsic lava is like cold peanut butter, barely moving at all, piling up in a thick, stubborn mass. The reason silica controls viscosity is beautifully logical. Those silicate tetrahedra we talked about, those tiny pyramids of silicon and oxygen, tend to link together. In felsic lavas, where there is a lot of silica, the tetrahedra form long, tangled chains and networks, like a bowl of molecular spaghetti. All those connections make the liquid thick and resistant to flow. In mafic lavas, where there is less silica and more metals like iron and magnesium, the tetrahedra are less connected. The liquid is looser, freer, more able to move. It is a lovely piece of chemistry, really. The behavior of an entire lava flow, whether it will creep slowly or rush forward, whether it will form smooth surfaces or jagged ones, all of that comes down to how many tiny pyramids of silicon and oxygen are linking together in the hot liquid. The microscopic shapes the macroscopic. The invisible governs the visible. And if that idea drifts away from you right now, that is perfectly all right. It will come back later, gently, in different words. For now, just hold on to the simplest version. More silica, thicker lava. Less silica, thinner lava. Dark lavas flow easily. Light lavas resist. That is enough. Beyond silica, lava contains a whole family of other elements. Aluminum is common, and it often sits in the middle of its own little atomic structures within the melt. Calcium, sodium, and potassium are abundant too, and they tend to occupy spaces between the silicate frameworks, like guests settling into the alcoves of a large, rambling house. Iron and magnesium, as we mentioned, are especially plentiful in mafic lavas, and they give those lavas their dark color and their relatively high density. There are also trace elements, tiny amounts of other substances that do not dominate the composition but leave their mark in subtle ways. Titanium, for example, is present in small quantities in many lavas, and it can influence the color of the minerals that form as the lava cools. Chromium, nickel, and cobalt are found in some lavas, carried up from deep in the mantle. Even elements like phosphorus, sulfur, and chlorine play roles, participating in chemical reactions within the melt, or escaping as gases when the lava reaches the surface. But we do not need to catalog every element tonight. The important thing is the feeling of richness, the understanding that lava is not a simple substance but a deeply complex one, full of chemical subtlety. Every flow of lava is a unique mixture, shaped by the particular conditions deep in the earth where it formed. And every rock that lava becomes, when it finally cools, is a frozen record of that mixture, a snapshot of a chemical moment millions of years in the making. For now, there is nothing you need to do with this information. Just let it settle, like sediment drifting to the bottom of a calm lake. The chemistry is there, holding everything together, and it will be there when we come back to it. Let us now imagine ourselves standing at a safe distance from a lava flow. The air is warm, and the ground beneath our feet is dark volcanic rock, old flows that cooled long ago. Ahead of us, the fresh lava is moving, slowly, almost imperceptibly, like a river of thick, glowing honey. And the surface of that flow has a texture, a particular character, that tells us a great deal about the chemistry within. One of the most common and most beautiful types of lava flow is called pahoeho. This is a Hawaiian word, and it describes a flow with a smooth, ropey surface. Imagine a thick liquid being poured slowly onto a flat surface, and as the outer layer cools, it wrinkles and folds into soft, rounded shapes, like ropes laid side by side. Pahoeho lava is typically mafic, basaltic, with low silica and high fluidity. It moves gently, and its surface cools into these lovely, undulating forms. If you were to run your hand over cooled pahoeho, it would feel smooth and rounded, almost organic, like the bark of an ancient tree. There is something deeply calming about pahoeho. It is lava at its most graceful, its most unhurried. The folds and ropes form because the outer skin of the flow cools and solidifies while the interior keeps moving, pushing the skin into gentle wrinkles. It is a slow dance between heat and cold, between liquid and solid, and the result is a surface that looks almost alive, frozen in mid-motion. Another type of flow, formed from the same basaltic lava but under slightly different conditions, is called AA. This is also a Hawaiian word, and it describes a flow with a rough, jagged, blocky surface. AA flows form when the lava is moving a bit faster, or when it has lost some of its gas, or when it has cooled just enough to become a little stiffer. The surface breaks apart into sharp, irregular chunks, like a field of dark, angular rubble. If pahoeho is the gentle version of basaltic lava, AA is the slightly more restless version, still the same chemistry, but expressed in a rougher texture. It is interesting that the same lava can produce both pahoeho and AA, depending on the conditions. A flow might start as smooth pahoeho near the vent and transition to rough AA further downslope as it cools and stiffens. The chemistry has not changed, but the physical conditions have, the temperature, the speed, the gas content, and so the texture transforms. It is a reminder that in geology, context matters as much as composition. For thicker, more silica-rich lavas, the flows take on a very different character. Block lava, for instance, forms from intermediate to felsic lavas with higher viscosity. Instead of smooth ropes or jagged fragments, block lava breaks into large, angular pieces with relatively flat surfaces. Imagine a giant paving stone that has been cracked into irregular chunks. The blocks are carried along on the surface of the flow, tumbling slowly, making a quiet, crunching sound as they shift and settle. And then there are lava domes, which form when very thick, very silica-rich lava reaches the surface but is too viscous to flow far. Instead, it piles up around the vent in a steep, rounded mound, like a very slow bubble of rock rising from the earth. Lava domes can grow over weeks, months, or even years, adding layer after layer of thick, sticky lava that cools and solidifies in place. They are among the most patient geological features, built incrementally, one slow extrusion at a time. There is a texture called pillow lava that forms when basaltic lava erupts underwater. As the hot lava meets the cold ocean water, the outer surface quenches almost instantly, forming a thin, glassy shell. But the interior is still molten, and it pushes outward, bulging the shell into a rounded, pillow-like shape. The pillow eventually breaks through, and a new pillow begins to form. Over time, these pillows accumulate in heaps and piles on the ocean floor, looking remarkably like stacks of oversized cushions made of dark glass and stone. Pillow lavas are found in many places around the world, and they are a sure sign that the rock was once erupted underwater. Ancient pillow lavas, millions or even billions of years old, have been found on land, lifted up by tectonic forces long after they formed on the sea floor. They are time capsules, preserving the shape and the chemistry of an ancient undersea eruption in solid rock. Each of these textures, the smooth ropes of Pahoho, the rough rubble of AA, the angular blocks, the patient domes, the rounded pillows, each one is a direct expression of the chemistry and the conditions of the lava that formed it. The silica content, the temperature, the gas content, the cooling rate. All of these factors combine to create a particular texture, a particular story written in stone. And as you lie there, perhaps you can picture these textures in your mind. Smooth, glowing surfaces folding like silk, dark, crunchy fields of rough rock, rounded pillows on the quiet ocean floor. Each one is a different mood of the same fundamental substance, molten rock meeting the world and becoming solid in its own particular way. In a moment, we will go even deeper into the microscopic world inside the lava itself. But for now, there is no hurry. Let the images of these flows settle in your mind, or let them drift away entirely. Either way, the earth keeps turning, the lava keeps cooling, and everything is exactly as it should be. Now, let us do something that requires a gentle shift of perspective. Let us shrink ourselves down in our imagination to the size of an atom, and let us enter the interior of a flow of molten lava deep within the glowing liquid, where the temperature is over 1,000 degrees and everything is in constant, slow motion. At this scale, the lava does not look like a river. It does not look like anything we would recognize as a liquid in our everyday experience. Instead, it is a vast, shimmering landscape of atoms and ions drifting and tumbling through a hot, chaotic ocean of energy. The most common atoms here are silicon and oxygen, and they are doing something beautiful. They are joining together in groups of 5, one silicon atom at the center, surrounded by 4 oxygen atoms at the corners, forming those silicate tetrahedra we talked about earlier. These tiny pyramids are everywhere, floating, bumping into each other, sometimes linking together at their corners to form chains and rings and sheets. Scattered among the silicate tetrahedra are ions of other elements, iron ions, with their characteristic weight and their tendency to absorb certain colors of light. Magnesium ions, smaller and lighter, slipping easily through the gaps in the silicate network. Calcium ions, sodium ions, potassium ions, each one occupying its own preferred position in the molecular crowd, each one contributing its own subtle influence to the properties of the melt. The whole mixture is in constant motion, but it is not chaotic in the way we might imagine. There is a kind of order to it, a tendency for certain atoms to cluster near each other, for certain configurations to persist for brief moments before dissolving and reforming. The ions vibrate and drift and rotate, and the silicate frameworks stretch and compress and rearrange, all driven by the enormous thermal energy of the melt. And then, as the lava begins to cool, something extraordinary starts to happen. Crystals begin to form. Somewhere in the melt, a few atoms find each other and lock into a regular, repeating pattern. Maybe it is a crystal of olivine made of magnesium, iron, silicon, and oxygen, arranged in a precise geometric lattice. The crystal is tiny at first, just a cluster of a few hundred atoms, barely detectable. But as the temperature continues to drop, more atoms are drawn to the growing crystal, snapping into place along its edges, adding layer after layer of perfectly ordered structure. You can think of crystallization as a kind of molecular tidying up. In the melt, everything is loose and disordered. But as the temperature falls, the atoms begin to settle into their lowest energy arrangements, their most comfortable positions, and those positions happen to form beautiful, geometric crystals. It is as if the atoms are slowly finding their seats in a vast concert hall, each one settling into the place where it fits best. The first crystals to form in a cooling lava are usually the minerals with the highest melting points. Olivine, for example, crystallizes at relatively high temperatures, around 1200 degrees Celsius. Its crystals are often small, green, and glassy, and they can be found embedded in basaltic lavas around the world. Pyroxene comes next, a family of minerals that form dark, stubby crystals. Then plagioclase feldspar, which forms lighter-colored, elongated crystals. Each mineral has its own temperature window, its own chemical preferences, and its own characteristic shape. As the lava cools further, more and more of the melt is consumed by crystallization. The remaining liquid becomes progressively richer in the elements that have not yet been incorporated into crystals, like silica, sodium, and potassium. This process is called fractional crystallization, and it is one of the most important mechanisms by which the chemistry of magma evolves over time. The liquid changes composition as crystals form and settle, and the resulting rock can be quite different from the original magma. But we are getting into details now, and there is no need to hold on to them too tightly. The point is simply this: inside every flow of lava, at the microscopic level, there is a quiet, ongoing transformation taking place. Atoms are finding order, crystals are growing. The chaotic liquid is slowly, patiently becoming solid rock, and each crystal that forms is like a tiny lantern, a perfect geometric structure glowing with the captured chemistry of the melt. If you could hold a thin slice of cooled lava up to the light and look at it through a microscope, you would see these crystals, arranged in patterns that are both random and beautiful. Some would be large and well-formed, with sharp edges and flat faces. The spaces between the crystals might be filled with glass, which is what happens when the melt cools too quickly for crystals to form. The atoms freeze in their disordered state, like dancers caught mid-step when the music stops. Volcanic glass is itself a fascinating substance. It is chemically identical to the crystalline minerals around it, made of the same silicon and oxygen and metals, but its atoms are arranged randomly, without the regular, repeating pattern of a crystal. Obsidian is the most famous volcanic glass, a smooth, dark, shiny material that forms when felsic lava cools very rapidly. Ancient peoples used obsidian to make tools and weapons, valuing its sharp edges and its beauty. But most lava does not cool fast enough to form pure glass. Instead, it produces a mixture of crystals and glass, a frozen record of the cooling process. The crystals tell us about the early stages of cooling, when the temperature was high and the melt was rich in certain elements. The glass tells us about the final moments when the remaining liquid froze in place, preserving whatever chemistry was left. And all of this is happening silently, invisibly, inside every lava flow that has ever existed on Earth. It is a hidden world of molecular precision and patient transformation, unfolding in the heat and the darkness of the rock, and now you know it is there, even if you forget the details. The crystals are growing. The glass is forming. The chemistry is organizing itself, atom by atom, into the solid earth beneath us. You can just listen as these ideas drift by. There is nothing you need to hold on to, nothing you need to remember for later. The microscopic world of lava is always there, doing its quiet work, whether anyone is watching or not. Let us now follow the lava a little further on its journey. We have watched it rise from the deep earth as magma. We have watched it emerge at the surface as lava. We have peered inside it at the atomic level and seen the crystals beginning to form. Now, let us watch it cool, slowly, patiently, and become rock. The type of rock that lava becomes depends on two things: its chemistry and the rate at which it cools. And both of these factors produce dramatically different results, which is one of the lovely things about igneous geology. The same basic ingredients can create wildly different rocks, depending on the circumstances of their cooling. Let us start with mafic lava, the dark, fluid, iron and magnesium-rich type. When mafic lava cools at the surface, it typically becomes basalt. Basalt is the most common rock on Earth's surface. It is dark, fine-grained, and dense. The crystals in basalt are usually very small because the lava cooled relatively quickly at the surface, not giving the minerals enough time to grow large. If you were to hold a piece of basalt in your hand, it would feel heavy and smooth, with a dark gray or black color, and you might not even be able to see the individual crystals without a magnifying glass. But if the same mafic magma cools slowly, deep underground, never reaching the surface, it produces a very different rock called gabbro. Gabbro has the same chemistry as basalt, the same minerals, but the crystals are much larger because the slow cooling gave them time to grow. A piece of gabbro looks like a mosaic of interlocking dark and light crystals, each one big enough to see with the naked eye. It is beautiful in a quiet, understated way, like a piece of abstract art made entirely of minerals. This relationship between cooling rate and crystal size is one of the most fundamental principles in igneous geology. Fast cooling produces small crystals, or even glass. Slow cooling produces large crystals. And the chemistry determines which minerals form, regardless of the crystal size. It is a simple rule, but it explains an enormous variety of rocks. For intermediate lavas, the surface rock is called andesite. Andesite is gray, often with a speckled appearance, and it is the signature rock of the great volcanic mountain ranges like the Andes, the Cascades, and the volcanoes of Japan and Indonesia. Its crystals are slightly larger than basalt, but still quite fine, and it often contains visible phenocrysts, which are larger crystals that began growing deep underground before the magma erupted. These phenocrysts are like passengers that hitched a ride from the deep, carried up to the surface, embedded in the flowing lava. If that same intermediate magma cools slowly underground, it becomes diorite, a coarser-grained rock with a salt and pepper appearance, made of interlocking crystals of plagioclase, feldspar, and dark minerals like hornblende and biotite. Diorite is a handsome rock, often used in construction and sculpture, and it can be found in the cores of ancient mountain ranges exposed by millions of years of erosion. And for felsic lavas, the surface rock is rhyolite, a light-colored, fine-grained rock that is the volcanic equivalent of granite. Rhyolite is relatively rare compared to basalt and andesite because felsic lava is so thick and sticky that it often does not flow far from the vent. Instead, it tends to pile up in domes or erupt in short, thick flows. Rhyolite can be pink, gray, or cream-colored, and it sometimes contains bands of different colors, showing the layers of lava that were squeezed out one after another. Granite, of course, is the deep, slow-cooled equivalent of rhyolite. It is perhaps the most familiar of all igneous rocks, with its characteristic speckled appearance of large, interlocking crystals of quartz, feldspar, and mica. Granite forms miles below the surface, where magma sits for thousands or millions of years, cooling at an almost imperceptible rate, giving the crystals time to grow to sizes you can easily see and even feel with your fingertips. Granite is the backbone of continents, the bedrock that underlies much of the dry land on Earth. There is something deeply reassuring about the patience of granite. It did not form in a rush. It formed over immense stretches of time, atom by atom, crystal by crystal, deep in the quiet darkness of the lower crust. And now it sits beneath us, solid and enduring, holding up the landscapes we live on. If there is a rock that embodies the idea of geological patience, it is granite. And between all these rocks, there are gradations, mixtures, and unusual varieties. There are rocks with porphyritic textures, where large crystals sit in a fine-grained matrix, showing a two-stage cooling history, slow at first, then fast. There are rocks with vesicular textures, full of tiny holes where gas bubbles were trapped as the lava solidified. Pumice is an extreme example, so full of gas bubbles that it can actually float on water. And there are glassy rocks, like obsidian, where the lava cooled so fast that no crystals formed at all. Each of these textures and rock types is a chapter in the story of cooling, and each one began as lava or as magma, a hot, complex chemical mixture rising from the deep earth. The chemistry set the stage. The cooling wrote the script. And the rock is the final performance, frozen in stone for us to discover millions or billions of years later. For now, you might imagine a lava flow somewhere in the world, cooling slowly in the night air. The surface has already hardened, forming a dark, glassy crust. But beneath that crust, the interior is still molten, still glowing faintly, still gradually surrendering its heat to the surrounding air and rock. Crystals are growing in the slowly cooling liquid. Gases are escaping in tiny wisps, and the flow is becoming, minute by minute, a new piece of the Earth's surface, a new rock, born from the fire of the deep. There is nothing you need to do with any of this. Just let the images float through your mind, or let them go entirely. The rocks will be there in the morning. The chemistry will still be true, and you can simply rest. Now we arrive at what might be the most enjoyable part of our journey. We are going to spend a long, unhurried time exploring some of the lesser-known facts about lava chemistry. These are the things that most people never learn, the hidden details, the quiet surprises that make the study of lava so endlessly fascinating to the scientists who dedicate their lives to it. We will take each fact gently, one at a time, like picking shells on a quiet beach. There is no hurry. Some of these may interest you. Some may drift past without leaving a trace. And that is exactly as it should be. Let us begin with the gases. We mentioned earlier that magma contains dissolved gases, mostly water vapor, carbon dioxide, and sulfur dioxide. But the story of these gases is far richer than a simple list of names. Water, for instance, is one of the most important dissolved components in magma, and its behavior is remarkable. At the enormous pressures deep inside the Earth, water dissolves readily into the silicate melt, sitting among the silicon and oxygen tetrahedra, breaking apart the long chains, and actually making the magma less viscous. Water in magma acts as a kind of lubricant, loosening the molecular structure and helping the liquid flow more easily. This means that the same magma, with the same silica content, can behave very differently depending on how much water it contains. A water-rich felsic magma might actually be more fluid than a dry one, because the water is disrupting all those tangled silicate chains. It is a subtle but important point, and it reminds us that chemistry is never just about what elements are present, but also about how they interact. As the magma rises and the pressure drops, the water begins to come out of solution, forming bubbles. This is exactly like what happens when you open a bottle of soda. The dissolved gas that was held in by pressure suddenly appears as fizz. In magma, these bubbles can grow and coalesce, and the rising gas can help drive the magma upward even faster. It is a gentle feedback loop. The rising magma releases gas, and the gas helps the magma rise. Carbon dioxide behaves differently from water in magma. It is less soluble, meaning it tends to come out of solution at greater depths, while the magma is still far underground. This means that CO2 bubbles often form early in the magma's ascent, while water bubbles form later, closer to the surface. The two gases have different personalities, in a sense, different preferences for when and where they make their exit from the melt. Sulfur is another fascinating player. In the melt, sulfur can exist in different chemical forms depending on the oxygen content of the magma. In reduced magmas, where there is less oxygen, sulfur tends to combine with iron to form tiny droplets of iron sulfide, little metallic beads that float through the melt like miniature planets in a glowing orange sky. In more oxidized magmas, sulfur bonds with oxygen to form sulfate, and when it escapes from the lava, it becomes sulfur dioxide gas, which has a sharp, distinctive smell. The volcanic gases that escape from lava flows and vents are a complex cocktail. Water vapor is the most abundant, typically making up 60 to 90% of the total. Carbon dioxide is the next most common. Then sulfur dioxide, hydrogen sulfide, hydrogen chloride, and hydrogen fluoride, each in smaller amounts. There are also traces of hydrogen, carbon monoxide, and various other compounds. The exact mixture depends on the chemistry of the magma and the conditions of the eruption. These gases may seem like a minor detail, but over the vast stretches of geological time, they have had an enormous impact on the Earth. We will come back to this idea later when we talk about how volcanic gases helped shape the atmosphere. But for now, just notice how much is happening inside a lava flow that we cannot see with our eyes. The gases are dissolving and exsolving, forming bubbles and escaping, carrying elements from the deep earth to the surface. It is a hidden ballet of chemistry, performed in the heat of the melt. Here is another quiet fact. The color of a lava flow and the color of the rock it becomes is determined by its chemistry. Dark lavas are dark because they are rich in iron and magnesium, elements that absorb visible light and give the rock its somber, brooding appearance. Basalt, the most common dark rock, owes its color primarily to minerals like pyroxene and olivine, which contain iron in their crystal structures. Lighter lavas are lighter because they contain more silica, more sodium, more potassium, and less iron. The minerals that crystallize from these lavas, like quartz and alkali feldspar, are naturally pale or translucent, and they scatter light rather than absorbing it. Rhyolite and granite, the felsic rocks, are typically pink, gray, or white for this reason. But color can also come from trace elements, present in very small amounts but with outsized effects. A tiny amount of chromium can make a mineral green. A trace of manganese can produce pink or purple tones. Iron, depending on its oxidation state, can be black, brown, red, or even green. And titanium, present in some volcanic minerals, can give them a deep, lustrous black appearance. There are also rare and unusual colors in the volcanic world. Some lavas, when they cool to form glass, have an iridescent sheen caused by the way light interacts with the internal structure of the glass. Fire obsidian, for example, displays layers of brilliant color, like oil on water, created by thin layers of different composition within the glass. Rainbow obsidian shows bands of green, purple, and gold. These are natural works of art, created by nothing more than chemistry and cooling. Here's a fact that many people find surprising. Lava has magnetic properties. The minerals that form as lava cools, particularly those containing iron, can become magnetized as they pass through a specific temperature called the Curie point. Above this temperature, the iron atoms are too energetic to maintain a permanent magnetic alignment. But as the rock cools below the Curie point, the magnetic domains within the iron-bearing minerals lock into place, aligned with the Earth's magnetic field at that moment. This means that every piece of cooled lava is a tiny compass, frozen in time, pointing toward the magnetic pole as it was when the rock solidified. By studying the magnetism of ancient lava flows, scientists can reconstruct the history of the Earth's magnetic field, tracking how the poles have wandered and even reversed over millions of years. The field of study is called paleomagnetism, and it has been one of the most powerful tools for understanding plate tectonics and the deep history of our planet. It is a remarkable idea, if you think about it. A lava flow that cooled 300 million years ago is still carrying, locked within its crystals, a memory of the direction of the magnetic pole at that exact time. The rock is a record keeper, an unwitting archivist of the Earth's invisible forces. And all of this from the simple chemistry of iron minerals cooling through a critical temperature. Let us visit another quiet corner of lava chemistry. The density of lava varies depending on its composition. Mafic lavas, rich in heavy elements like iron and magnesium, are denser, typically around 2,700 to 3,000 kilograms per cubic meter. Felsic lavas, lighter in composition, are less dense, perhaps around 2,300 to 2,500 kilograms per cubic meter. This difference in density has important consequences for how lavas flow and where they end up. Denser lavas tend to stay low, filling valleys and depressions, flowing along the path of least resistance. Lighter lavas, being thicker and stickier, tend to pile up near their source. Over geological time, this simple density difference has helped shape the distribution of rock types on the Earth's surface. The ocean floors are made of dense, dark basalt because the thin, fluid, mafic lava that erupts at mid-ocean ridges flows out evenly across the seafloor. The continents, by contrast, are made largely of lighter, felsic rocks like granite, which have accumulated over billions of years through a complex process of melting, crystallization, and tectonic recycling. Here is something else that is not widely known. The viscosity of lava is not just determined by its silica content. Temperature also plays a crucial role. As lava cools, even by just a few tens of degrees, its viscosity can increase dramatically. The silicate tetrahedra begin to link together more tightly. The molecular structure becomes more rigid, and the liquid becomes thicker and slower. This is why a lava flow that starts out smooth and fluid near the vent can become rough and sluggish further downslope, even though its chemical composition has not changed. Crystal content matters too. As crystals form within the cooling lava, they act like obstacles in the flow, increasing the effective viscosity of the mixture. A lava with 20 or 30% crystals behaves very differently from one with just a few percent. It is stiffer, grainier, more resistant to movement. At some point, when the crystal content reaches about 50 or 60%, the mixture transitions from a liquid with suspended crystals to a crystal-rich mush that can barely move at all. This is the point where lava effectively stops being lava and starts being rock, even though some pockets of melt may linger for a long time in the spaces between the crystals. And here is a gentle, dreamy fact to carry with you. Some lavas contain tiny inclusions of other materials, trapped inside crystals as they grew. These inclusions are called melt inclusions, and they are like time capsules. A growing crystal may trap a tiny droplet of the surrounding melt, sealing it inside as the crystal continues to grow around it. That droplet preserves the exact composition of the melt at the moment it was captured, undisturbed by any later changes. By studying melt inclusions, scientists can peer back in time and learn what the magma was like at different stages of its journey. They can measure the dissolved gas content, the trace element concentrations, and the temperature and pressure at which the crystal formed. Each inclusion is a message in a bottle, sent from the depths of the earth and opened in a laboratory millions of years later. It is one of the most beautiful and precise tools in all of volcanology, and it all depends on the simple act of a crystal growing around a tiny drop of liquid. There is also the question of how lava behaves differently on land versus underwater. We touched on this briefly with pillow lavas, but the differences go deeper. When lava erupts on the seafloor, the enormous pressure of the overlying water suppresses the release of dissolved gases. This means that underwater lava tends to be less vesicular, with fewer bubbles than lava that erupts in air. The water also causes the outer surface of the lava to cool extremely rapidly, forming a thick, glassy rind that insulates the hot interior. This rapid quenching produces a material called hyaloclastite when the glass fragments and crumbles, forming a chaotic mixture of angular glass shards and pillow fragments. Hyaloclastite is common around underwater volcanoes and along mid-ocean ridges, and it can be found on land wherever ancient submarine volcanic rocks have been uplifted. It is a rough, dark, crumbly material, and it tells a story of fire meeting water in the deep ocean. The chemistry of the lava itself can be affected by contact with seawater. Water can infiltrate the cooling rock, reacting with the minerals and altering their composition. Iron can be oxidized, turning dark minerals red or brown. New minerals can form, replacing the original volcanic ones. This process, called hydrothermal alteration, is most intense near hot springs on the seafloor, where superheated seawater circulates through the newly formed rock, dissolving some elements and depositing others. Over time, these reactions can significantly change the chemistry of the volcanic rock, turning fresh basalt into a rainbow of altered minerals. Let us stay with the ocean for a moment, because there is one more lovely fact about undersea lava. At mid-ocean ridges, where tectonic plates are pulling apart, magma wells up from the mantle to fill the gap, creating new oceanic crust. This is the single largest source of lava on Earth, producing far more molten rock each year than all the world's land-based volcanoes combined. And yet, because it happens at the bottom of the ocean, far from human eyes, it goes almost entirely unnoticed. The lava that erupts at mid-ocean ridges is almost always basaltic, with a remarkably consistent composition around the world. Scientists call it MORB, which stands for mid-ocean ridge basalt. MORB is the default lava of the Earth, the most common type of volcanic rock produced by the planet, and its chemistry provides a baseline against which all other lavas are compared. It is low in silica, rich in iron and magnesium, and relatively poor in elements like potassium and sodium. It is, in a way, the simplest expression of the mantle's chemistry, a direct window into the composition of the Earth's interior. As you rest here, you might find it soothing to think about this. Somewhere right now, at the bottom of an ocean you may never visit, lava is quietly emerging from the Earth, building new crust, adding to the planet's surface. It happens without fanfare, without witnesses, in the cold, dark water miles below the waves. And it has been happening for billions of years, a slow, steady heartbeat of the planet measured in basalt. Let us shift now to the mantle itself, the great hot layer of rock that lies beneath the crust and makes up the bulk of the Earth. The composition of the mantle has a profound influence on the chemistry of the lavas that it produces, and understanding this connection is one of the great challenges and great pleasures of geology. The mantle is made mostly of a rock called peridotite, which is rich in the mineral olivine, a green, glassy crystal made of magnesium, iron, silicon, and oxygen. Peridotite is denser and more refractory, meaning more resistant to melting than the rocks of the crust. It does not melt all at once. Instead, when conditions are right, only a fraction of the peridotite melts, and that partial melt is what rises to become magma. The chemistry of the partial melt depends on how much melting occurs and what conditions drive it. At mid-ocean ridges, decompression melting occurs as the mantle rises toward the surface, and the reduction in pressure allows a small percentage of the rock to melt. This produces the basaltic MORB we just discussed. At subduction zones, where one tectonic plate dives beneath another, Water released from the sinking plate lowers the melting point of the mantle above it, producing a different suite of magmas that tend to be more silica-rich and more volatile. And at hot spots, like the one beneath Hawaii, a plume of unusually hot mantle material rises from deep within the earth, perhaps from near the core mantle boundary. This extra heat produces larger volumes of melt and can generate lavas with distinctive trace element signatures that differ from MORB. The lavas of hotspot volcanoes are windows into the very deepest parts of the mantle, carrying chemical messages from thousands of kilometers below. It is remarkable, when you think about it, that we can learn about conditions thousands of miles beneath our feet by studying the chemistry of a rock at the surface. The lava is a messenger, carrying information from the deep earth to where we can reach it, study it, and understand it. Every trace element, every isotopic ratio, every mineral grain is a clue to the conditions in the mantle at the time and place where the magma formed. And by reading these clues, scientists have built a picture of the Earth's interior that is astonishingly detailed, considering that no one has ever been there. But that is more than enough detail for now. Let all of these facts settle gently, like snowflakes falling onto a still pond. Some will melt immediately. Some might linger, and that is all perfectly fine. For now, there is nothing you need to do, nothing you need to understand. Just rest and let the quiet chemistry of the earth keep turning in the background. As you lie there, breathing slowly, let us expand our view even further. Let us leave the earth for a while and visit some other worlds in our solar system where lava has also played a role. Because the chemistry of molten rock is not unique to our planet. It is a universal process, occurring wherever rocky bodies are hot enough to melt, and the story of lava on other worlds is as vast and quiet as space itself. Let us start with the moon, our nearest neighbor. The moon is a small, quiet world today, with no active volcanoes and no flowing lava. But it was not always so. Billions of years ago, in the early history of the solar system, the moon was volcanically active, and its surface was shaped by enormous flows of basaltic lava that filled the great impact basins and created the dark, flat plains we can see from Earth. These plains are called maria, from the Latin word for seas, because early astronomers, seeing their dark, smooth surfaces through telescopes, thought they might be bodies of water. The lunar maria are made of basalt, very similar in many ways to the basalt on Earth. The chemistry is broadly comparable, rich in iron and magnesium, and low in silica. But there are differences. Lunar basalts have no water in their minerals because the moon is almost entirely devoid of water. They also contain more titanium than most terrestrial basalts, giving some of them a distinctive dark blue-black appearance. And because the moon has no atmosphere and no weathering, the surfaces of these ancient lava flows are still beautifully preserved, battered only by the slow rain of micrometeorites over billions of years. When the Apollo astronauts visited the moon in the late 1960s and early 1970s, they brought back samples of lunar basalt that have been studied intensively ever since. These rocks are among the most precious scientific specimens on Earth, and they have taught us an enormous amount about the moon's history, its interior, and the conditions of the early solar system. The chemistry of those small, dark rocks connects us to a time when the moon was young and hot, when lava flowed freely across its surface, filling vast basins and building the familiar face we see in the night sky. You might imagine, as you drift here, the surface of the moon in that ancient time, a dark, airless landscape lit by the distant sun and by the glow of the lava itself. No sound, of course, because there is no atmosphere to carry it, just the slow, silent spread of molten basalt across a gray plain, cooling under the stars. It is an image of extraordinary calm, a volcanic eruption with no thunder, no roar, just the quiet chemistry of silicon and oxygen and iron doing what it does on every rocky world. Now let us visit Mars. Mars is a world of contrasts, with vast deserts, towering volcanoes, and deep canyons, all shaped in part by volcanic activity that occurred billions of years ago. The largest volcano on Mars, and indeed the largest in the entire solar system, is Olympus Mons. It is a shield volcano built up over millions of years by countless flows of basaltic lava, each one adding a thin layer to the gently sloping sides. Olympus Mons is about 22 kilometers tall and over 600 kilometers wide. It is so large that if you were standing on its slopes, you would not be able to see either the summit or the base, because the curvature of the planet would hide them from view. The volcanic rocks on Mars are broadly basaltic, like those on Earth and the Moon, but Mars has its own chemical personality. Martian lavas tend to be richer in iron than terrestrial ones, which is part of the reason the Martian surface has that distinctive reddish color. The iron in the volcanic rocks has been oxidized by exposure to the thin Martian atmosphere, forming iron oxide, or rust, that gives the red planet its name. Mars also has extensive lava plains, called planitia, that cover large areas of the northern hemisphere. These plains were formed by massive basaltic eruptions that spread lava across the surface in thin, fluid sheets, much like the flood basalts on Earth. The chemistry of these lavas tells us about the composition of the Martian mantle and the thermal history of the planet, how hot it was, how much it melted, and when the volcanism finally ceased. And it may not have entirely ceased. There is evidence that some volcanic features on Mars are relatively young, perhaps only a few million years old, which in geological terms is practically yesterday. Whether Mars is still volcanically active somewhere deep beneath its surface is an open question, one that future missions may help to answer. For now, the giant volcanoes stand silent under a butterscotch sky, monuments to a fiery past that shaped an entire world. Let us journey a little farther, out beyond Mars, past the asteroid belt, to the realm of Jupiter and its many moons. One of those moons, a small, tormented body called Io, is the most volcanically active object in the entire solar system. Io is roughly the size of our moon, but it is anything but quiet. Its surface is constantly being reshaped by volcanic eruptions that are unlike anything on Earth. The volcanism on Io is driven by tidal heating. Jupiter's enormous gravitational pull, combined with the competing tugs of the other large moons, squeezes and stretches Io's interior, generating enormous amounts of heat through friction. This heat keeps the interior partially molten and drives nearly continuous volcanic activity. The lavas on Io are extraordinary. Some of them appear to be even hotter than the hottest lavas on Earth, perhaps exceeding 1600 degrees Celsius. These superheated lavas may be composed of ultramafic materials, very low in silica and very rich in magnesium, similar to the komatiite lavas that erupted on Earth billions of years ago, but are no longer produced by our cooler modern mantle. If this is true, then Io is a window into a style of volcanism that our own planet has long since outgrown. The surface of Io is a patchwork of vivid colors, yellows, reds, oranges, blacks, and whites, created by sulfur and sulfur dioxide deposits from the volcanic gases. The lava flows themselves are dark, but they are quickly coated and buried by the sulfurous deposits that rain down from the volcanic plumes. It is a strange and beautiful world, endlessly renewing itself, endlessly burying its own past under layers of fresh volcanic material. And yet, even on Io, the fundamental chemistry is the same. Silicate minerals, silicon and oxygen tetrahedra, melting and crystallization. The processes that govern lava chemistry on Earth operate throughout the solar system, wherever rocky material is hot enough to melt. The specific compositions differ, the temperatures vary, the conditions are exotic, but the underlying chemistry is universal. It is one of the great unifying themes of planetary science. There are other volcanic worlds too, each with its own chemical story. Venus, shrouded in thick clouds, has a surface that is largely covered in basaltic lava, plains, and volcanic features, suggesting a volcanic history that may still be active today. Enceladus, a tiny moon of Saturn, has cryovolcanoes that erupt not lava but water and ice, a different kind of volcanism but governed by the same principles of heat, pressure, and phase change. And Triton, the largest moon of Neptune, has dark plumes of nitrogen, gas, and dust erupting from its frigid surface, a form of volcanism so cold that it seems almost paradoxical. The universe is full of worlds where the chemistry of molten material has shaped the landscape, and on every one of them, the same basic elements, silicon, oxygen, iron, magnesium, and the rest, are participating in the same ancient dance of melting and freezing, rising and cooling that we see on Earth. It is a thought that can make you feel connected to something much larger than yourself, a chemistry that spans not just the Earth but the entire cosmos. But for now, you are here, on this particular world, in this particular moment, resting comfortably, and the lava of other worlds can wait. Let the planets drift by in your imagination, each one glowing faintly with its own volcanic warmth, and let them go. There is nothing you need to do but breathe and rest, and let the slow chemistry of the universe turn around you. Now, gently, let us bring our attention back to Earth, because the chemistry of lava is not just an interesting scientific topic. It is, in a very real sense, the story of our planet. The Earth we live on, the air we breathe, the ground beneath our feet, all of it has been shaped over billions of years by the chemistry of molten rock. Let us start at the very beginning, or as close to the beginning as we can get. When the Earth formed, about 4.5 billion years ago, it was an extremely hot world. The energy of accretion, the heat from countless collisions of smaller bodies, and the decay of radioactive elements within the young planet all contributed to temperatures high enough to melt large portions of the Earth. In those earliest times, the planet may have been largely or entirely molten, a vast sphere of magma orbiting the young Sunday. As the Earth slowly cooled, the heaviest elements, mostly iron and nickel, sank to the center, forming the core. The lighter silicate materials rose to the outside, forming the mantle and eventually the crust. This process, called differentiation, was driven by gravity and density, the same simple principles that govern the separation of oil and water, and it was fundamentally a chemical process, a sorting of elements based on their affinities and their densities. The first solid crust that formed on Earth was probably basaltic, similar to the ocean floors today. It was dark, dense, and thin, and it was constantly being recycled back into the mantle by the vigorous convection currents that stirred the young planet. Over time, through a long and complex series of melting, crystallization, and remelting events, lighter, more silica-rich rocks began to accumulate at the surface. These lighter rocks were the seeds of the continents, and they gradually grew over billions of years into the landmasses we know today. This process of continental growth is still happening. Every time a volcano erupts, it adds a tiny amount of new material to the surface. Every time a subduction zone recycles oceanic crust back into the mantle, some of the lighter elements are left behind, added to the overlying continental crust. It is an incredibly slow process, measured in millimeters per year at best, but over the vast stretches of geological time, it has built entire continents. The ground you are lying on tonight is the accumulated product of billions of years of lava chemistry. And then there are the gases. We talked earlier about the gases dissolved in magma, water vapor, carbon dioxide, sulfur dioxide, and others. Over the history of the Earth, the cumulative release of these gases from volcanic eruptions has had an enormous impact on the planet's atmosphere and oceans. The Earth's early atmosphere was very different from the one we have today. It was rich in carbon dioxide and water vapor, with little or no free oxygen. These gases came primarily from volcanic outgassing, the slow, steady release of dissolved gases from erupting lavas over hundreds of millions of years. The water vapor eventually condensed to form the oceans. The carbon dioxide helped create a greenhouse effect that kept the young Earth warm enough for liquid water to exist. And the sulfur and other gases participated in complex chemical cycles that helped regulate the composition of the atmosphere over time. In a very real sense, the air you are breathing right now has its origins in the chemistry of ancient lavas. The oxygen in the atmosphere was produced later by photosynthetic organisms, but the canvas on which that oxygen was painted, the nitrogen, the argon, the trace gases, much of that came from the deep earth, carried to the surface by magma and released through volcanic vents. The oceans, too, owe their existence largely to volcanic outgassing. The water that fills the world's ocean basins was once dissolved in magma, trapped in the silicate melt under enormous pressure. As that magma erupted and cooled over billions of years, the water was released, molecule by molecule, into the atmosphere, where it eventually condensed and fell as rain. The oceans are, in essence, the accumulated, exhaled breath of the Earth's volcanoes, collected over geological time. It is a profoundly beautiful idea. Every glass of water you have ever drunk, every raindrop, every snowflake, every wave in the sea, all of it traces back through a long and winding chemical path to the interior of the Earth. The water was born in the melt, carried upward by buoyancy, released at the surface, and gathered into the great bodies of water that make our planet unique in the known solar system. There is a concept in geology called the rock cycle, which describes how rocks are constantly being created, destroyed, and recreated over geological time. Igneous rocks form from cooling lava or magma. They are weathered and eroded into sediment, which is compacted into sedimentary rock. Sedimentary rock can be buried and heated until it transforms into metamorphic rock. And metamorphic rock, if heated enough, can melt again, becoming magma once more. The cycle continues endlessly, turning and returning over millions and billions of years. Lava chemistry plays a central role in this cycle. Every time magma forms and erupts, it brings new material from the deep earth to the surface, refreshing the supply of elements available for weathering, erosion, and biological processes. And every time surface rocks are subducted back into the mantle, they carry with them the chemical signatures of everything that has happened to them. The weathering, the deposition of sediment, the interactions with water and life. These returning chemicals influence the next generation of magma, completing the loop. This cycling of material in and out of the mantle is sometimes described as the Earth's slow breathing. Outgassing at the surface is the exhalation, releasing gases and fresh rock. Subduction is the inhalation, drawing surface material back into the deep interior. The cycle is immensely slow, measured in hundreds of millions of years, but it is continuous and essential. Without it, the Earth's surface would gradually become depleted of the elements that sustain life, and the atmosphere and oceans would slowly lose their character. So when you think about lava, you are not just thinking about a hot, glowing substance that emerges from volcanoes. You are thinking about one of the fundamental engines that drives the chemistry of our entire planet. The lava is part of a vast, slow, patient system that has been operating for as long as the Earth has existed, and that will continue operating for billions of years to come. And all of it, every cycle, every eruption, every crystal, every bubble of gas, is governed by the same basic chemistry that we have been exploring tonight. Silicon and oxygen forming tetrahedra, metals arranging themselves among the silicate frameworks, gases dissolving and exsolving, crystals nucleating and growing. These simple processes, repeated countless times over unimaginable timescales, have built the world you live on. There is something deeply restful in that idea. The Earth is patient. It does not rush. It does not worry. It simply continues its slow chemical work, building and recycling and renewing, one atom at a time. And you, resting here tonight, are part of that same story. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged in stars, delivered to the earth, and cycled through the mantle and the crust over billions of years. You are made of the same elements as lava. You are part of the same chemistry. Let that thought settle gently, or let it go. There is nothing you need to do with it. It is simply true, a quiet fact about the universe, as unremarkable and as astonishing as a crystal forming in cooling rock. We have covered so much ground tonight, and yet there is always more. The world of lava chemistry is vast, and we have only touched on a fraction of what there is to know. But this is a bedtime journey, not an exam, so let us continue at the same gentle pace, exploring a few more quiet corners before we begin to wind down. Let us talk for a moment about something called lava tubes. When a basaltic lava flow moves across the landscape, the outer surface cools and hardens, forming a solid crust. But beneath that crust, the interior remains molten and continues to flow. Over time, the flowing lava can drain out from beneath the hardened surface, leaving behind a hollow tunnel, a lava tube. These tubes can be enormous, stretching for miles, with ceilings as high as a cathedral and walls of smooth, dark basalt. Inside a lava tube, the chemistry of the walls tells a story. The surface of the tube may be coated in a thin layer of volcanic glass, formed where the outermost layer of lava cooled most rapidly against the air inside the tube. Below that glassy skin, the basalt becomes more crystalline, as the cooling was slower. Stalactites of basalt may hang from the ceiling, formed by the last drips of molten rock before the tube drained. And on the floor, there may be a smooth, rippled surface, frozen mid-flow, like a river of stone caught in the act of moving. Lava tubes are fascinating environments for many reasons, not least because they exist on other worlds as well. There are lava tubes on the Moon and Mars, formed by the same process of surface crusting and interior drainage. Some scientists have proposed that these extraterrestrial lava tubes could serve as shelters for future human explorers, providing natural protection from radiation and extreme temperatures. It is a lovely thought that the same quiet chemistry that builds basalt tubes on Earth might one day provide homes for people on the Moon. Here is another soft fact for your drifting mind. The temperature of lava, when it first reaches the surface, varies depending on its composition. Mafic basaltic lavas are the hottest, typically between about 1,000 and 1,200 degrees Celsius. Intermediate andesitic lavas are a bit cooler, around 900 to 1,100 degrees. And felsic rhyolitic lavas are the coolest, if you can call 700 to 900 degrees cool, which of course in any normal sense you cannot. But in the world of lava, these differences in temperature are significant because they affect the viscosity, the gas behavior, and the mineralogy of the flow. The color of the glowing lava is directly related to its temperature, just as the color of a heated piece of metal in a blacksmith's forge changes from red to orange to yellow to white as it gets hotter. The coolest lavas glow a deep, dark red, almost cherry-colored. Hotter lavas glow bright orange. The hottest lavas can appear almost yellow or even white at their freshest. As the lava cools, the glow fades from bright to dim, from orange to red to a dull, barely visible crimson, and finally to the dark, unlit surface of solid rock. If you have ever seen footage of flowing lava, you may remember that glow, that deep, warm, pulsing light. It is one of the most mesmerizing sights in all of nature, and it is nothing more than thermal radiation, the photons emitted by atoms vibrating with heat energy. The chemistry of the lava determines its temperature, and the temperature determines the color of the glow. It is physics and chemistry working together to create something beautiful. Let us also spend a moment with a type of volcanism that is particularly gentle: effusive volcanism. Effusive eruptions are the kind that produce lava flows rather than violent explosions. They occur most commonly with mafic, low viscosity lavas that can flow easily out of the vent and spread across the landscape. The Hawaiian volcanoes are the most famous examples of effusive volcanism, producing long, sinuous rivers of basaltic lava that move slowly enough that a person could walk alongside them. Effusive eruptions can last for months or even years, steadily adding new rock to the surface. They are the patient kind of volcanism, building new land one layer at a time. Over thousands and millions of years, these layers accumulate into broad, gently sloping shield volcanoes, like Mauna Loa and Kilauea in Hawaii. Shield volcanoes are the largest type of volcano by volume, but they are also the gentlest in profile. Their slopes so gradual that from a distance they look like vast, dark domes resting on the landscape. The chemistry of shield volcano lavas is remarkably consistent. Flow after flow of basaltic lava, each with a similar composition, each adding its thin layer to the growing mountain. The source magma comes from the hot spot deep in the mantle, rising steadily and erupting with a regularity that is almost meditative. There is a rhythm to it, a slow pulse of heat and rock, repeated over and over across millions of years. We should also say a few words about something called volcanic glass, because it is one of the most intriguing products of lava chemistry. We mentioned obsidian earlier, but volcanic glass takes many forms. Pumice, for instance, is a volcanic glass that is full of gas bubbles, so many that the rock is often light enough to float on water. It forms when frothy, gas-rich felsic lava is ejected into the air and cools rapidly, trapping the bubbles inside. The result is a pale, rough, lightweight stone that looks almost like a solidified foam. Pele's hair is another form of volcanic glass, named after the Hawaiian goddess of fire. It consists of extremely thin strands of basaltic glass, formed when droplets of lava are stretched by the wind into long, golden, hair-like threads. These threads can be carried great distances by the wind, and they accumulate in delicate, shimmering tangles on the ground. Pele's tears are similar, but instead of being stretched into threads, the droplets solidify into small, rounded beads of dark glass. Each of these glassy forms is a product of rapid cooling, so rapid that the atoms in the melt did not have time to arrange themselves into crystals. The glass preserves the disordered atomic arrangement of the liquid, frozen in place. Over very long timescales, millions of years, volcanic glass can slowly devitrify, which means it gradually transforms from glass into tiny crystals, the atoms finally finding their ordered positions. But this process is so slow that most volcanic glass we encounter is still essentially as glassy as the day it formed. Here is one more quiet fact, and then we will begin to slow down even further. The chemical composition of lava can change over the lifetime of a single eruption. As magma is drawn from a chamber and erupted at the surface, the remaining magma in the chamber continues to cool and crystallize. The crystals that form selectively remove certain elements from the melt, enriching the remaining liquid in others. This means that the lava erupted early in a sequence may have a different composition from the lava erupted later. For example, the early lavas might be more mafic because the original magma was rich in iron and magnesium. But as olivine and pyroxene crystals form and settle to the bottom of the chamber, the remaining melt becomes progressively more felsic, richer in silica and alkali elements. Later eruptions from the same chamber might produce more silica-rich lavas with different minerals, different viscosity, and different textures. This process, called magmatic differentiation, is one of the key mechanisms by which the diversity of igneous rocks is generated from a single parent magma. It is a slow, patient process, occurring over thousands or tens of thousands of years within the magma chamber, and it produces an elegant progression of rock types that geologists can trace and reconstruct. It is like watching an artist mix colors on a palette, starting with a single tube of paint and gradually creating a whole spectrum of shades. And with that, we have explored another quiet corner of lava chemistry. The facts may blur together now, and that is fine. They are not going anywhere. The chemistry continues in the dark, in the deep, in the slow, patient interior of the earth, and you are welcome to let it continue without you for now. Let us linger a while longer in this space between waking and sleeping. The science we have explored tonight is vast, and there are still gentle details waiting to be noticed, like small stones on a quiet shore that you did not see at first glance. Consider the mineral olivine, which we have mentioned a few times. Olivine is one of the most abundant minerals in the Earth's upper mantle, and it is one of the first minerals to crystallize from a cooling basaltic melt. Its name comes from its color, a beautiful, translucent green that ranges from pale lime to deep forest, depending on the ratio of iron to magnesium in its crystal structure. More magnesium gives a lighter green. More iron gives a deeper, richer tone. When olivine crystals are large enough and clear enough, they are considered gemstones, and the gem form of olivine is called peridot. Peridot has been valued for thousands of years, and it is one of the few gemstones that comes in only one color, green, though the shade can vary. Ancient Egyptians called peridot the gem of the sun, and they mined it on a small volcanic island in the Red Sea. The chemistry is simple: magnesium, iron, silicon, and oxygen, arranged in a particular way, but the result is a stone of quiet, luminous beauty. On some beaches in the world, particularly in Hawaii and a few other volcanic islands, the sand is green because it is made almost entirely of tiny olivine crystals, weathered out of the basaltic lava by the waves. These green sand beaches are rare and ephemeral, because olivine weathers relatively quickly compared to other minerals. The iron in the olivine reacts with water and oxygen, and the crystals gradually break down. A green sand beach is a temporary phenomenon, geologically speaking, lasting only as long as the supply of fresh, olivine-rich rock continues to replenish the sand faster than weathering can remove it. It is a gentle reminder that even stones are temporary. Given enough time, even the hardest rock will dissolve, grain by grain, atom by atom, returning its elements to the soil, the water, and the air. The chemistry of lava does not end when the rock cools. It continues, slowly, through weathering and erosion, as the rock interacts with the world around it and gives back what it borrowed from the deep earth. Let us also think about the role of aluminum in lava chemistry, because it is often overlooked in favor of the more dramatic elements like iron and magnesium. Aluminum is actually one of the most abundant elements in the Earth's crust, and it plays a crucial role in the structure of many silicate minerals. In the silicate melt, aluminum can substitute for silicon in the tetrahedral positions, sitting at the center of an oxygen tetrahedron and becoming part of the aluminosilicate framework. This substitution has important effects on the properties of the melt. When aluminum replaces silicon, it changes the charge balance of the framework, because aluminum has a different number of positive charges than silicon. To compensate, additional cations like sodium, potassium, or calcium are needed to balance the charge. These cations sit in the spaces between the tetrahedra, acting as stabilizers and modifying the viscosity and other properties of the liquid. The feldspar minerals, which are the most abundant mineral group in the Earth's crust, are all aluminosilicates. They come in several varieties: plagioclase feldspars, which range from calcium-rich to sodium-rich, and alkali feldspars, which are potassium-rich. Together, the feldspars make up more than half of the Earth's crust by volume. Every piece of granite, every piece of andesite, every piece of basalt contains feldspar, and the particular type of feldspar present tells us about the chemistry of the magma from which the rock formed. It is a quiet kind of importance. Feldspar does not sparkle or catch the eye the way quartz or olivine does. It is usually pale, sometimes white, sometimes pink or gray, and it breaks along flat surfaces called cleavage planes. But without feldspar, the Earth's crust would be a very different place. The continents, which are largely made of feldspar-rich rocks, owe their existence to this humble mineral and the aluminum that helps to build it. Here is something else that is worth knowing, in a drowsy, half-attentive sort of way. The isotopes of certain elements in lava can tell scientists where the magma came from and what happened to it along the way. Isotopes are atoms of the same element that have slightly different masses because they have different numbers of neutrons in their nuclei. Most elements have several stable isotopes, and the ratios between these isotopes can vary depending on the geological processes that the material has undergone. For example, the isotopes of strontium and neodymium in a lava sample can reveal whether the magma was derived from the depleted upper mantle, which has been partially melted many times, or from a more primitive, less processed source deeper in the earth. Lead isotopes can trace the involvement of ancient continental crust, which has a distinctive lead isotope signature that differs from the mantle. Oxygen isotopes can show whether the magma interacted with surface water or sediments on its way up. These isotopic tools are incredibly powerful, allowing scientists to trace the origins and evolution of magma with remarkable precision. And yet, the measurements themselves are extraordinarily delicate, requiring sensitive instruments and painstaking laboratory work. A slight change in the ratio of two isotopes, measured to several decimal places, can reveal a journey of thousands of kilometers through the Earth's interior. It is a testament to the patience and ingenuity of geochemists, and to the richness of the information encoded in every drop of lava. But you do not need to remember any of these details. They are here simply as part of the landscape of ideas, like wildflowers along a path that you are walking very slowly in the fading light. Some you notice, some you pass by, and the path continues either way. Let us talk about one more topic before we begin our long, slow descent towards sleep. Let us think about time, geological time, because the chemistry of lava operates on timescales that are almost impossible for the human mind to grasp, and there is something deeply calming about trying to hold those timescales in your thoughts. The oldest rocks on Earth are about 4 billion years old, formed not long after the planet itself coalesced from the dust and gas of the early solar system. Some of those oldest rocks are igneous, formed from lavas that erupted onto the surface of a world that was still violently hot and geologically active. The chemistry of those ancient lavas is preserved in the rocks, a chemical snapshot of the Earth in its infancy. Between then and now, lava has erupted on Earth continuously, not in the same place, of course, and not at a constant rate, but always somewhere, at mid-ocean ridges, at subduction zones, at hot spots, at continental rifts. The Earth has never stopped producing lava. It is a 4 billion-year-old chemical factory, drawing material from its deep interior and laying it down at the surface, endlessly, tirelessly, with a patience that dwarfs anything in human experience. Imagine 4 billion years. It is roughly a third of the age of the universe. In that time, the Earth has gone from a molten ball of rock and metal to a world of oceans, continents, ice caps, forests, and cities. And through all of it, the chemistry of lava has been at work, building, recycling, and renewing the surface. The continents have drifted and collided and split apart. The oceans have opened and closed. Mountain ranges have risen and been worn flat. Species have appeared and gone extinct, and the lava has kept flowing, a steady thread connecting the ancient Earth to the present one. There is no need to worry about any of this. The timescales are so vast that they are beyond worry. They are beyond urgency. They are beyond any human emotion at all. They are simply time, passing, as it always does, one moment after another, one crystal after another, one slow flow of rock after another, and you are here, in this moment, resting. The earth will continue its work while you sleep. Let us consider, too, the idea that the ground beneath you is not as solid as it seems. We tend to think of rock as the ultimate solid, the foundation of everything, but on geological timescales, rock flows. The mantle, which is solid rock, flows very slowly in convection currents driven by the heat of the core. It moves at a rate of a few centimeters per year, about the same speed that your fingernails grow. But over millions of years, those centimeters add up to thousands of kilometers, enough to carry continents across the globe and reshape the surface of the planet. This slow flow of solid rock is what drives plate tectonics, the grand mechanism that creates mountains, opens oceans, and produces most of the world's volcanic activity. And at every stage of the process, lava chemistry is involved. The melting of the mantle produces magma. The eruption of magma produces lava. The cooling of lava produces rock. The recycling of rock back into the mantle completes the circle. It is all chemistry, operating at planetary scales and geological timescales, a quiet, enormous, beautiful machine. And you are part of it. Not in an active, conscious way, but simply by being here, on this planet, made of these elements, breathing this air, drinking this water. You are a temporary arrangement of atoms that have been cycling through the earth for billions of years. The iron in your blood may have once been in a lava flow. The calcium in your bones may have once been in a feldspar crystal deep in the mantle. You are, in a very literal sense, a product of lava chemistry, rearranged and animated by the improbable magic of life. That is a thought you can hold or release. It changes nothing either way. The chemistry continues, the earth turns, and you rest. As we continue this long, gentle night together, let us revisit a few of the ideas we have explored, not to test your memory, but simply to let them wash over you again, like the slow return of a wave on a quiet beach. Lava is molten rock. It begins as magma, deep inside the earth, in the hot, pressurized chambers of the lower crust and upper mantle. It is a mixture of silicate melt, tiny crystals, and dissolved gases. When it reaches the surface, we call it lava. When it cools, it becomes igneous rock. And the particular chemistry of the lava, how much silica it contains, what metals are dissolved in it, how much gas it carries, all of this determines what kind of rock it will become and what textures it will have. Silica is the key player. More silica makes thicker, stickier lava. Less silica makes thinner, more fluid lava. This is because the silicate tetrahedra, those tiny pyramids of silicon and oxygen, link together more extensively when there is more silica, forming a tangled molecular network that resists flow. With less silica, the network is looser, and the liquid moves more freely. The mafic lavas, dark and iron-rich, flow like slow rivers and cool into basalt. The felsic lavas, light and silica-rich, barely move at all and cool into rhyolite. The intermediate lavas are somewhere in between, and they produce andesite. These three broad categories cover most of the volcanic rocks on Earth, and they correspond to different geological settings, different temperatures, and different depths of origin in the mantle. And within each of these categories, there is endless variation. No two lava flows are exactly alike. Each one carries its own unique chemical fingerprint, shaped by the particular conditions deep in the earth where the magma formed. The trace elements, the isotope ratios, the mineral assemblages, all of these details make each flow unique, a one-of-a-kind chemical event in the long history of the planet. Let us think once more about the crystals. As lava cools, atoms and ions begin to arrange themselves into orderly, repeating patterns, forming crystals. The first crystals to appear are the ones with the highest melting points, minerals like olivine and pyroxene. As the temperature continues to drop, more minerals join in, each crystallizing at its own characteristic temperature. The sequence of crystallization follows a predictable pattern, described by something called Bowen's reaction series, which maps out the order in which common silicate minerals form from a cooling melt. Bowen's reaction series is one of the foundational concepts in igneous petrology, and it is named after Norman Levi Bowen, a Canadian geologist who worked in the early 20th century. Bowen conducted careful laboratory experiments, melting and cooling silicate mixtures under controlled conditions, and he showed that the minerals crystallize in a specific, reproducible order. Olivine first, then pyroxene, then amphibole, then biotite, and at the low temperature end, muscovite, quartz, and the alkali feldspars. You do not need to memorize this series. It is enough to know that it exists, that there is an orderly progression to the way crystals form from a cooling melt, and that this progression is driven by the fundamental chemistry of the elements involved. Each mineral crystallizes when the temperature reaches the point where the atoms can no longer remain disordered. They settle into their crystal positions like tired travelers finding their beds at an inn. First the heaviest sleepers, then the lighter ones, until everyone is at rest. Let us also revisit the gases one more time, because they are such an important and often overlooked part of lava chemistry. The dissolved gases in magma, primarily water vapor, carbon dioxide, and sulfur dioxide, are present in relatively small amounts, typically a few percent by weight, but their influence on the behavior of the magma is vastly out of proportion to their abundance. Water, as we discussed, reduces the viscosity of the melt, making it more fluid. It also lowers the melting point of the rock, which means that the presence of water can cause rock to melt at temperatures where it would otherwise remain solid. This is why the mantle above subduction zones, where water is released from the descending oceanic plate, produces so much magma. The water acts as a flux, a melting aid, allowing the mantle to produce melt that would not otherwise exist. Carbon dioxide, though less soluble than water, plays a role in the early stages of magma ascent. As we mentioned, CO2 comes out of solution at greater depths, forming bubbles that can help drive the magma upward. These bubbles are like tiny engines, adding buoyancy to the rising magma and helping it push through the surrounding rock. Buoyancy to the rising magma and helping it push through the surrounding rock. Sulfur has its own complex chemistry within the melt. In addition to forming iron sulfide droplets in reduced magmas, sulfur can also bond with oxygen to form sulfate, which is more common in oxidized magmas. The partitioning of sulfur between sulfide and sulfate, and its eventual release as volcanic gas, has important implications for the Earth's atmosphere and climate. Large volcanic eruptions can inject massive amounts of sulfur dioxide into the stratosphere, where it forms tiny sulfuric acid droplets that reflect sunlight and temporarily cool the planet. But that is a story for another time. Or perhaps it is a thought that can simply dissolve into the quiet of this moment. There is a type of lava that we have not yet mentioned, and it deserves a quiet moment of its own. Carbonatite lava is one of the rarest and most unusual volcanic materials on Earth. Unlike almost all other lavas, which are based on silicate minerals, carbonatite lava is composed primarily of carbonate minerals. Essentially, it is molten limestone. It is extremely fluid, more fluid than any silicate lava, and it erupts at much lower temperatures, around 500 to 600 degrees Celsius. The only active carbonatite volcano on Earth is Old Doinyo Lengai in the East African Rift in Tanzania. Its lavas are so unusual that they appear almost black when freshly erupted, but they turn white within hours as they react with moisture in the air. The carbonate minerals are hygroscopic, meaning they absorb water readily, and this reaction changes their appearance and their structure. It is a volcano that produces lava unlike anything else on the planet, a singular chemical curiosity that reminds us how much variety the Earth is capable of. Carbonatite magmas are thought to originate from the melting of carbonate-bearing rocks in the mantle under very specific conditions of temperature and pressure. They are rare because those conditions are themselves rare. But when they do occur, the result is a lava that challenges all of our usual assumptions about what molten rock should look like and how it should behave. It is a reminder that nature is always capable of surprising us, even in a field as well studied as volcanology. Let us also spend a moment with the concept of volcanic provinces, the large-scale regions of the Earth where volcanic activity has been particularly intense over geological time. Some of the most impressive volcanic provinces are the large igneous provinces, or lips, which are vast outpourings of basaltic lava that cover hundreds of thousands of square kilometers. The Deccan Traps in India, the Siberian Traps in Russia, and the Columbia River basalts in the northwestern United States are all examples of large igneous provinces. These were formed by enormous volumes of basaltic lava erupting over relatively short geological timescales, perhaps 1 million years or so. The lava flows stacked up in layers, hundreds of meters thick in some places, burying the landscape beneath a blanket of dark basalt. The chemistry of these flood basalts is broadly similar to MORB, but with some distinctive features. They tend to have slightly higher concentrations of certain trace elements, suggesting that they originated from deeper or more enriched sources in the mantle. Some scientists believe that large igneous provinces are produced by mantle plumes, rising columns of hot material from the deepest mantle, similar to the plumes that produce hotspot volcanoes like Hawaii, but on a much larger scale. The formation of a large igneous province is one of the most dramatic events in the Earth's geological history, and there is evidence that some of them coincided with mass extinction events. The exact mechanisms by which massive volcanism might cause extinction are still debated, but the release of enormous quantities of volcanic gases, particularly carbon dioxide and sulfur dioxide, into the atmosphere is thought to have played a role, altering the climate and the chemistry of the oceans. But we are not dwelling on catastrophe tonight. We are simply noting, with calm interest, that the chemistry of lava operates on scales from the microscopic to the planetary, and that its effects can be felt across the entire biosphere. The same chemistry that grows tiny crystals in a cooling melt can, when amplified to planetary scale, reshape the entire surface of the Earth. It is all connected, from the atom to the continent, from the crystal to the climate. And now, as we approach the final stretches of our journey, let us return to the idea that began this night. Lava is simply molten rock. It is made of silicon and oxygen, plus metals like iron, magnesium, calcium, sodium, potassium, and aluminum. It rises from the deep earth because it is lighter than the surrounding solid rock. It cools and becomes stone, and in the process, it builds the surface of our planet, one flow at a time, one crystal at a time, one atom at a time. There is nothing urgent about any of this. There is nothing you need to do, nothing you need to remember, nothing you need to worry about. The Earth's chemistry operates on time scales that are beyond human comprehension, and it will continue to operate long after we are gone. The lava will keep flowing. The crystals will keep forming. The gases will keep cycling. And the planet will keep breathing, slowly and patiently, as it has for 4.5 billion years. Let us take one more slow, wandering turn through the landscape of lava chemistry. Picture yourself, if you can, standing in a lush green field somewhere in the tropics. The soil beneath your feet is dark and rich, and the plants growing in it are vigorous and tall. This soil, this living layer of earth, was created by the weathering of volcanic rock. Basaltic lava erupted perhaps tens of thousands of years ago, has been broken down by rain, by roots, by microorganisms into a deep, fertile soil that nourishes everything growing in it. Volcanic soils are among the most fertile in the world. The basaltic rock is rich in the mineral nutrients that plants need: iron, magnesium, calcium, potassium, phosphorus. As the rock weathers, these elements are released into the soil in forms that plant roots can absorb. This is why so many volcanic regions, from the slopes of Mount Etna in Sicily to the highlands of Central America to the islands of Indonesia, are renowned for their agricultural productivity. The chemistry of lava, transformed by weathering, becomes the chemistry of life. It is a beautiful cycle. The elements that were locked in the mantle, carried to the surface by magma, erupted as lava, and cooled into rock, are now feeding the roots of a coffee plant, or a banana tree, or a rice paddy. The atoms of iron and magnesium that once drifted through a silicate melt at 1200 degrees are now part of a leaf, absorbing sunlight and converting it to sugar. The chemistry has changed its form, but the elements are the same. They have simply moved from one chapter of their long story to another. And while we are thinking about the connections between lava chemistry and the living world, let us consider the deep ocean floor. At mid-ocean ridges and around underwater volcanoes, hot water circulates through the newly formed basaltic crust, reacting with the rock and dissolving metals and other elements. This water, heated to hundreds of degrees and enriched with dissolved minerals, eventually returns to the ocean through hydrothermal vents, chimney-like structures on the seafloor that belch plumes of dark, mineral-laden fluid into the frigid water. These hydrothermal vents support extraordinary communities of organisms that live entirely without sunlight. The base of the food chain is not photosynthesis, but chemosynthesis, the process by which certain bacteria harvest energy from the chemical reactions between the vent fluids and the surrounding seawater. The bacteria oxidize hydrogen sulfide, methane, and other chemicals released from the volcanic rock, and they use the energy to build organic molecules, feeding the tube worms, clams, crabs, and shrimp that cluster around the vents. The chemistry of lava, in this case, becomes the chemistry of an entire ecosystem. The elements dissolved from the basalt, the sulfur, the iron, the manganese, the zinc, are the fuel that powers life in one of the most extreme environments on Earth. These vent communities were only discovered in the late 1970s, and they have revolutionized our understanding of where and how life can exist. Some scientists believe that similar vent systems may have been the cradle of life on Earth, the place where the first living cells emerged from the interactions between volcanic chemistry and seawater billions of years ago. It is a profound thought, and one that connects lava chemistry to the deepest questions about our own existence. But it is not a thought that requires any effort or anxiety. It is simply another of the many quiet revelations that emerge when you look closely at the world of molten rock. The chemistry of lava is not just the chemistry of stone. It is the chemistry of soil, of water, of air, of life itself. It touches everything. Let us rest with that thought for a moment. Let it be like a stone dropped into a still pond, creating ripples that spread outward and gradually fade into stillness. The connections between lava chemistry and the rest of the world are vast and intricate, but they need not be overwhelming. They are simply there, like the stars above you on a clear night, countless and beautiful and beyond any need for you to count or name them. As you lie here, the world outside is turning. Somewhere, at this very moment, lava is flowing. Perhaps on the flanks of a Hawaiian shield volcano, a thin stream of basalt is creeping across an old lava field, adding one more layer to the growing island. Perhaps at the bottom of the Atlantic Ocean, along the mid-Atlantic ridge, fresh basalt is quietly erupting onto the seafloor, pushing the Americas and Europe a tiny bit farther apart. Perhaps on Io, far out in the cold reaches of the outer solar system, a massive eruption is sending a plume of sulfur and silicates high above the surface, painting the little moon in new colors. And perhaps none of that is happening right at this exact second, but it was happening recently, and it will happen again soon, because the Earth and the other volcanic worlds are always at work. The chemistry never stops. The heat never fully dissipates. The slow, patient processes of melting and crystallization continue, as they have for billions of years and will for billions more. You are welcome to imagine any of these scenes, or none of them. You are welcome to think about the chemistry, or to let it all go and simply enjoy the feeling of being still and warm and safe. This narration has been a long, gentle river of ideas, and like any river, it will eventually find the sea. We are almost there now. As we drift further into this quiet night, let us explore a few more gentle corners of the volcanic world. There is no urgency to any of this. We are simply wandering, the way you might wander through a garden in the last light of the day, pausing here and there to notice something beautiful. Let us think about the way lava interacts with water, not just in the deep ocean, but at the shore, where rivers of molten basalt meet the sea. In places like Hawaii, where active lava flows sometimes reach the coast, the meeting of fire and water creates something remarkable. The lava enters the ocean and is instantly quenched, shattering into fragments of volcanic glass and sand. Steam rises in great white plumes. The water hisses and churns, and on the seafloor, just below the surface, new land is being built, grain by grain, fragment by fragment. Over time, these fragments accumulate into deltas and beaches of black sand. Black sand beaches are found in many volcanic regions around the world, and they owe their color to the same iron-rich minerals that give basalt its dark hue. The sand grains are tiny pieces of volcanic glass and crystal, each one a miniature sample of the lava that produced it. If you were to pick up a handful of black sand and look at it under a magnifying glass, you would see glittering fragments of glass, tiny crystals of olivine and pyroxene, and perhaps a few grains of magnetite, the iron oxide mineral that gives some volcanic sands a slightly metallic sheen. There is something soothing about the idea of black sand. It is a reminder that even destruction, even the violent meeting of fire and water, produces something beautiful and gentle. A beach, a place to rest. A place where the chemistry of the deep earth is laid out in tiny grains beneath your feet, warmed by the sun, cooled by the waves. Let us now think about something called xenoliths. A xenolith is a piece of rock that has been caught up in a body of magma and carried along for the ride. The word comes from Greek, meaning foreign rock, and that is exactly what it is, a stranger in a strange land, a fragment of one rock type embedded in another. Xenoliths are valuable to geologists because they provide direct samples of rocks that would otherwise be inaccessible. Some xenoliths come from the deep crust, carried up by ascending magma. Others come from the mantle itself, plucked from the walls of the magma's pathway and transported to the surface. Mantle xenoliths are particularly precious because they are among the only direct samples we have of the Earth's interior. These mantle xenoliths are typically made of peridotite, that olivine-rich rock we mentioned earlier. They are often green, dense, and coarse-grained, with large crystals of olivine, pyroxene, and sometimes garnet. When you hold a mantle xenolith in your hand, you are holding a piece of rock that was formed hundreds of kilometers below the surface, in conditions of extreme pressure and temperature, and was carried to the surface in a matter of hours or days by a rising column of magma. It is a message from the deep earth, delivered by volcanic express. Some xenoliths are so fresh, so unaltered by their journey through the magma, that they preserve the exact mineralogy and chemistry of the mantle at the depth where they originated. Scientists study these rocks intensely, measuring their mineral compositions, their trace element concentrations, and their isotopic ratios, all in an effort to understand the conditions deep inside the planet. Each xenolith is a data point, a single observation in the vast, ongoing project of understanding the Earth's interior. And there is something quietly wonderful about the idea of the Earth sending up these little packages of itself, wrapped in lava, for us to find and study. It is as if the planet is sharing its secrets, one rock at a time, with anyone patient enough to look. Let us also consider the phenomenon of lava lakes. A lava lake is exactly what it sounds like, a body of molten lava that sits in a volcanic crater or caldera, sometimes for years or even decades. The surface of a lava lake is a mesmerizing sight. It is dark and crusted, like the skin on a cup of hot cocoa, but the crust is constantly breaking apart and reforming as the liquid beneath it circulates slowly. Through the cracks, you can see the bright orange glow of the molten rock below, pulsing gently with the convection currents that stir the lake. Lava lakes are relatively rare on Earth. Only a handful exist at any given time. Some of the most famous include the lava lake at Kilauea in Hawaii, the lava lake at Nyiragongo in the Democratic Republic of Congo, and the lava lake at Erta-Ale in Ethiopia. Each of these lakes has its own character, its own chemistry, and its own rhythm of activity. Some are relatively quiet, gently turning over their surface crust in slow, regular cycles. Others are more active, with bursts of spattering and fountaining as gas bubbles rise to the surface and burst. The chemistry of a lava lake is continuously evolving. As the surface crust cools and sinks back into the lake, it carries cooler, partially crystallized material back into the melt, mixing it with the hotter liquid below. Fresh, hot magma may also be supplied from below, feeding the lake and keeping it molten. The result is a complex, dynamic chemical system that is constantly adjusting itself, a natural laboratory where the processes of melting, crystallization, and gas release can be observed in real time. Scientists have learned a great deal from studying lava lakes. By measuring the temperature, the gas emissions, and the surface dynamics of these lakes, they can gain insights into the behavior of magma that would be impossible to observe any other way. A lava lake is a window into the inner workings of a volcanic system, a rare opportunity to watch the chemistry of molten rock in action, right at the surface. If you can, imagine a lava lake at night. The surrounding landscape is dark and still. The lake glows softly, its surface a mosaic of dark crust and bright orange cracks. The light pulses gently, like a heartbeat. There is a faint sound of hissing and crackling as the crust shifts and reforms. It is one of the most peaceful and hypnotic sights in the natural world, a living portrait of the Earth's inner heat, held in a quiet basin of stone. Here is another gentle topic for your drowsy consideration. The speed at which lava flows varies enormously, depending on its chemistry, its temperature, its slope, and its volume. The fastest basaltic lava flows, on steep slopes, can move at speeds of several kilometers per hour, fast enough to outpace a slow walk, but still much slower than most people imagine. The average speed of a typical basaltic flow is more like walking pace, or even slower. Felsic lava flows are much slower still. A thick, sticky rhyolitic flow might advance only a few meters per day, or even less. Lava domes can take weeks or months to grow to their full size, expanding almost imperceptibly, like a very slow balloon being inflated with rock. The longest lava flows on Earth stretch for hundreds of kilometers. The Undara lava tubes in Australia, for example, were formed by a massive basaltic eruption about 190,000 years ago. The lava flowed for over 160 kilometers, following river valleys and filling depressions, before finally cooling and solidifying. The tubes that it left behind are some of the longest and best preserved in the world. And on the Moon and Mars, lava flows can be even longer. Without an atmosphere to cool the lava, and with lower gravity to slow it down, basaltic lava on these worlds can travel extraordinary distances. Some lunar lava channels, called rials, stretch for hundreds of kilometers across the surface, tracing the paths of ancient flows that erupted billions of years ago. They are frozen rivers of stone, preserved perfectly in the airless, weatherless lunar environment. Let us now visit a topic that is both simple and profound: the heat of the Earth. All of the volcanic activity we have discussed tonight, every flow of lava, every eruption of gas, every crystal growing in a cooling melt, all of it is ultimately driven by the heat of the Earth's interior. And that heat has two main sources. The first source is primordial heat, the heat that was generated when the Earth formed. The collisions of the countless small bodies that accumulated to build the planet released enormous amounts of energy, much of which is still stored in the interior. The differentiation of the core, when heavy iron sank to the center and lighter materials rose, also released gravitational energy that was converted to heat. This primordial heat has been slowly leaking away for 4.5 billion years, but the Earth is large and well insulated, so a great deal of it remains. Together, these two heat sources maintain the Earth's internal temperature at levels high enough to keep the mantle convecting, the plates moving, and the magma forming. They are the engine that drives everything we have talked about tonight. Every flow of lava, from the first eruptions on the young Earth to the ones happening right now, draws its energy from this deep, ancient heat. And this heat is finite. Very slowly, over billions of years, the Earth is cooling. The radioactive elements are gradually decaying, producing less heat over time. The primordial heat is slowly dissipating. Eventually, in the very distant future, the Earth's interior will cool to the point where volcanic activity ceases, plate tectonics stops, and the planet becomes geologically quiet, like Mars today. But that time is billions of years away, far beyond any time frame we need to concern ourselves with. For now, the heat is abundant, the magma is flowing, and the chemistry of lava continues its patient work. Here is a soft, curious fact about something called columnar jointing. When a thick flow of basaltic lava cools, it contracts, and the contraction creates cracks that propagate downward from the surface. Under ideal conditions, these cracks form a remarkably regular pattern of hexagonal columns, like a giant honeycomb made of stone. The columns can be several meters tall and tens of centimeters wide, and they stack together so precisely that they look almost artificial, as if they were carved by a careful hand. The most famous example of columnar jointing is the Giant's Causeway in Northern Ireland, where thousands of basalt columns form a dramatic coastal landscape. According to legend, the columns were built by a giant named Finn McCool as a pathway across the sea. But the real explanation is even more remarkable. They are the natural result of the physics of cooling and contraction, operating on a uniform, chemically homogeneous lava flow. The hexagonal pattern emerges because it is the most efficient way to divide a contracting surface into equal-sized units, minimizing the total length of the cracks. Nature, as always, finds the most elegant solution. Similar columnar basalt formations can be found all over the world. Devil's Tower in Wyoming is a striking example, a monolithic column of rock with dramatic vertical columns on its sides. The Organ Pipes in Victoria, Australia, and Svartafoss Waterfall in Iceland, with its dark, hanging columns behind a cascade of glacial meltwater, are other beautiful instances. Each of these formations tells the same chemical story. A thick, basaltic flow, cooling slowly and uniformly, contracting into the most efficient pattern geometry allows. There is something deeply satisfying about columnar jointing. It is mathematics and chemistry and physics all working together, without any human intervention, to create something of extraordinary beauty. And it happens silently, underground, over the weeks and months that a thick lava flow takes to cool. No one sees it happen. The columns are only revealed later, when erosion strips away the surrounding rock and exposes the hidden geometry beneath. It is nature's secret architecture, built in the dark and revealed in the light. Let us also spend a few quiet moments thinking about the relationship between volcanoes and the water cycle. We have already discussed how volcanic outgassing contributed the water that fills the Earth's oceans. But the connection between volcanism and water goes even deeper than that. Water is constantly being recycled between the surface and the interior of the Earth. At subduction zones, oceanic crust that has been soaked in seawater for millions of years is carried down into the mantle. The water in the rock is released as the plate descends and heats up, and it rises into the overlying mantle, lowering the melting point and generating new magma. This water-enriched magma eventually erupts, releasing the water back to the atmosphere. The water then condenses, falls as rain, runs into rivers, enters the ocean, soaks into the oceanic crust, and eventually returns to the mantle at a subduction zone. It is a vast, slow cycle, measured in hundreds of millions of years. This deep water cycle is essential for maintaining the Earth's surface environment. Without the constant return of water from the interior, the oceans would gradually be lost, absorbed into the mantle, and never returned. And without the subduction of water back into the mantle, the generation of magma at subduction zones would cease, and the growth of continents would slow or stop. The water cycle and the rock cycle are intimately linked, each one sustaining the other in a long, patient exchange of material between the surface and the deep. It is a comforting thought. In a way, the Earth takes care of itself. The cycles are self-sustaining, self-regulating, operating without any external guidance or direction. The water flows, the rock melts, the lava cools, the gases escape, the rain falls, and the cycle begins again. It has been this way for billions of years, and it will continue for billions more. There is a deep geological peace in that continuity. Let us think for a moment about the colors that volcanic minerals produce. We have mentioned that basalt is dark because of its iron-rich minerals, and that felsic rocks are lighter because of their silica-rich, iron-poor minerals. But within these broad categories, there is a wonderful range of specific colors, each one tied to a particular mineral or a particular chemical condition. Olivine, as we have discussed, is green. Its color comes from the interaction of iron atoms in the crystal structure with visible light. The iron absorbs certain wavelengths and transmits others, producing the characteristic green that has made peridot a prized gemstone for millennia. Pyroxene, a common mineral in mafic and intermediate rocks, is typically dark green to black. Its color, too, comes from iron, but in a different crystal structure that absorbs light differently from olivine. Augite, the most common pyroxene in volcanic rocks, is usually nearly black, giving basalt much of its dark color. Plagioclase feldspar, the most abundant mineral in the Earth's crust, ranges from white to gray. In its purest calcium-rich form, it can be almost transparent. In its sodium-rich form, it tends to be white or pale gray. These light-colored feldspar crystals are what give andesite and granite their lighter appearance, contrasting with the dark pyroxene and olivine. Quartz, which is pure silica, is colorless in its pure form but can take on a variety of colors from trace impurities. Amethyst, for example, is purple quartz, colored by tiny amounts of iron that have been irradiated by natural radiation in the surrounding rock. Rose quartz gets its pink color from microscopic inclusions of a mineral related to dumortierite. Smoky quartz is brown or gray, colored by the effects of radiation on aluminum impurities in the crystal. And then there are the accessory minerals, present in small amounts but often spectacularly colored. Apatite can be green, blue, or yellow. Zircon can be colorless, red, orange, or blue. Titanite, also called sphene, can produce brilliant yellow or green crystals. Even in a dull-looking piece of volcanic rock, there may be hidden treasures, tiny crystals of extraordinary color, visible only under a microscope or in a polished, thin section. The colors of volcanic minerals are, in essence, the visible expression of chemistry. Each color is produced by a specific arrangement of atoms interacting with light in a specific way. It is quantum mechanics made tangible, the behavior of electrons in crystal fields translated into the greens, blacks, whites, pinks, and purples that we see in volcanic rocks. And like so much else in the world of lava chemistry, it is both scientifically precise and naturally beautiful. As you rest here, perhaps you can imagine a collection of volcanic rocks arranged on a table, a piece of dark, glassy obsidian, a rough, lightweight chunk of pumice, a smooth, rounded piece of basalt with tiny green olivine crystals embedded in it, a polished slice of granite showing its interlocking crystals of quartz, feldspar, and mica, a fragment of andesite, gray and speckled, with a few larger crystals of plagioclase. Each rock is a different chapter of the same story, the story of molten rock cooling into solid stone, and each one carries within it the chemical fingerprint of the magma that produced it. You do not need to hold this image. You do not need to remember these rocks or their names. They are simply here, in this moment, like the background of a dream that may or may not follow you into morning. The chemistry is gentle, the rocks are patient, and you are free to let go of everything. There is one more phenomenon worth mentioning as we continue our slow, sleepy exploration, and that is the concept of magma mixing. Sometimes, two different batches of magma, with different chemistries and temperatures, come into contact with each other within a magma chamber or a conduit. When this happens, the two magmas begin to mix, blending their chemical compositions together. Magma mixing can produce hybrid lavas with intermediate compositions, combinations that would not have formed from a single parent magma. The resulting rocks sometimes show evidence of the mixing in their textures. You might see two different types of crystals, one set from the original mafic magma and another from the felsic one, sitting side by side in the same rock. Or you might see bands of different colored rock swirling together like marble, showing the incomplete mixing of two different melts. These mixed rocks are beautiful, both visually and scientifically. They are snapshots of a chemical encounter, two different liquids meeting and mingling, each bringing its own elements and minerals to the blend. The mixing is never quite complete, because the two magmas have different viscosities and temperatures, and the contrast between them creates interesting textures and mineral assemblages that geologists can study to reconstruct the mixing event. Magma mixing is thought to be an important trigger for some eruptions. When a fresh batch of hot, volatile-rich magma enters a chamber containing cooler, partially crystallized magma, the injection of heat and gas can remobilize the older magma and drive it toward the surface. It is a gentle push. In geological terms, one body of liquid encouraging another to move, and the result can be an eruption that brings both magmas to the surface together. Let us think, too, about the sounds of a lava flow. Although we cannot hear them through this narration, real lava flows produce a variety of quiet, fascinating sounds. The cracking and tinkling of cooling crust, like the sound of breaking ceramic or the gentle chiming of glass. The low, rumbling hiss of gas escaping through vents and cracks. The soft, rhythmic crunching of AA blocks tumbling over each other at the advancing front of a flow. And, very occasionally, the deep, almost musical resonance of lava tubes vibrating as the molten rock flows through them. Volcanologists sometimes use acoustic monitoring to study volcanic activity, listening for changes in the frequency and intensity of the sounds produced by the magma and gas within a volcanic system. These sounds, called volcanic tremor, are a kind of pulse, a continuous vibration produced by the movement of magma and fluids through the underground plumbing of a volcano. By listening to these sounds, scientists can sometimes detect changes in activity before they become visible at the surface. It is a lovely thought that the earth has its own quiet music, produced by the movement of molten rock through stone, and that we have learned to listen to it. The frequencies are often too low for human hearing, deep bass notes that rumble through the rock like the slow breathing of a sleeping giant. But with sensitive instruments, we can hear them, and in those sounds, we can read the chemical and physical conditions of the magma below. We have been talking for a long time now, and the night has deepened around us. If you are still awake, that is fine. If you have drifted into sleep and returned, that is fine too. The script of this journey has no chapters that must be caught in order. You can drop in and out like a stone skipping across water, touching the surface here and there, and each touch is complete in itself. Let us consider one more quiet topic, the idea that the Earth's volcanic activity has changed over time. The early Earth, in the first billion years or so of its existence, was much more volcanically active than it is today. The interior was hotter, the mantle convected more vigorously, and the rate of magma production was much higher. Some of the most extreme lavas in the geological record, the ultramafic komatiites we mentioned earlier, erupted during this period, when mantle temperatures were several hundred degrees hotter than today. As the Earth has slowly cooled over billions of years, volcanic activity has gradually declined. The types of lavas produced have changed, too. Komatiites, those extremely hot, extremely fluid, magnesium-rich lavas, have not been produced for about 2.5 billion years, because the mantle is no longer hot enough to generate them. The volcanism of the modern Earth is more moderate, more refined, if you will, producing the familiar basalts, andesites, and rhyolites that we have discussed tonight. But even this modern volcanism is not static. The rate of volcanic activity fluctuates over tens of millions of years, influenced by the arrangement of the continents, the vigor of mantle convection, and other deep-seated factors. There have been periods of intense volcanism, like the Great Flood basalt events, and periods of relative quiet. The Earth's volcanic pulse has a rhythm, slow and irregular, but unmistakable when viewed across the sweep of geological time. In the very distant future, as we mentioned, the Earth will eventually cool to the point where volcanic activity ceases entirely. This will happen billions of years from now, long after the sun has exhausted its hydrogen fuel and begun to expand. The last lava flow on Earth is still far in the future, an event that no human will ever witness. But it will come eventually, and the planet will settle into a quiet geological retirement, its chemical work done. There is no sadness in this thought. It is simply the way of things. Everything in the universe has a lifespan, from atoms to stars to planets. The Earth's volcanic lifespan is measured in billions of years, which is generous by any standard. And in those billions of years, the chemistry of lava will have built the continents, filled the oceans, shaped the atmosphere, nourished the soil, and supported the extraordinary diversity of life that has flourished on this small, warm, restless world. As you drift here, between waking and sleeping, let these long timescales cradle you. The urgency of the day is gone. The worries of the week are distant and muted. There is only this moment, this quiet breath, this gentle chemistry turning in the dark beneath you. The Earth is warm and patient. The lava is flowing somewhere. The crystals are growing. And you are here, part of it all, resting in the long, slow story of the planet. Let us spend one more lingering while on a topic that brings together many of the threads we have woven tonight, the way lava chemistry tells time. Geologists have developed an extraordinary set of tools for determining the age of volcanic rocks, and these tools are based, at their core, on the chemistry of the lava. The most widely used method is radiometric dating, which relies on the decay of radioactive isotopes within the minerals of the rock. When a mineral crystallizes from a cooling melt, it incorporates certain radioactive isotopes into its crystal structure. From that moment on, those isotopes begin to decay at a known, constant rate, transforming into different, stable isotopes. By measuring the ratio of parent to daughter isotopes in a mineral grain, scientists can calculate how much time has passed since the crystal formed. Potassium-argon dating, for example, uses the decay of potassium 40 to argon 40. Potassium is a common element in many volcanic minerals, and argon, being a noble gas, tends to escape from the melt, but is trapped within crystals once they form. By measuring the amount of argon 40 that has accumulated in a volcanic rock, scientists can determine when the rock cooled and solidified. This method has been used to date everything from recent lava flows to ancient basalts billions of years old. Uranium lead dating is another powerful technique, particularly for very old rocks. It uses the decay of uranium isotopes to lead isotopes within the mineral zircon, which is remarkably resistant to alteration and can survive even when the surrounding rock is metamorphosed or melted. A single zircon crystal, smaller than a grain of sand, can provide a precise age for the volcanic event that produced it, accurate to within a few million years even for rocks that are billions of years old. These dating techniques have been instrumental in constructing the geological timescale, the framework that organizes the entire history of the Earth. Every boundary between geological periods, every milestone in the evolution of life, every great environmental change, many of these have been dated using volcanic rocks and the radioactive clocks they contain. The chemistry of lava, it turns out, is not just a story of elements and minerals. It is a story of time itself, written in isotopes, readable only with the most sensitive instruments and the most patient analysis. And that is, perhaps, the most remarkable thing about lava chemistry. It tells us not just what the Earth is made of, but when things happened, how long they lasted, and what the conditions were at every stage. It is a chronicle of the planet, written in the language of atoms and crystals, and it is still being written, even now, in every lava flow that cools and every crystal that grows. You do not need to understand radiometric dating to appreciate this. You do not need to know the half-life of potassium 40 or the crystal structure of zircon. These are details for the scientists, the patient, dedicated people who spend their lives reading the chemical story of the Earth. What you can take from this, if you take anything at all, is the simple, calming thought that the Earth keeps a record of itself. Every moment is preserved somewhere, in some rock, in some crystal, in some ratio of isotopes too subtle for the eye to see but clear enough for an instrument to read. The Earth remembers, and you are welcome to forget, to let go, to rest. The records are safe, the chemistry is preserved, and the story will be there in the morning, patient and unchanging, waiting for anyone who wants to read it. Before we begin to slow our pace even further, let us wander through a few more gentle territories of volcanic science. Each of these is a small, self-contained meditation, and you are free to let any or all of them pass by unnoticed. Let us think about volcanic islands. Many of the most beautiful islands on Earth are entirely volcanic in origin, built from the seafloor up by successive eruptions over millions of years. Hawaii, Iceland, the Galapagos, the Canary Islands, Reunion, Tahiti, the Azores, all of these were created by lava, layer upon layer, rising from the ocean floor until they broke the surface and became dry land. The chemistry of these island-building lavas is predominantly basaltic, the same low silica, iron-rich chemistry that produces the ocean floors. But as an island grows and its magma system matures, the chemistry can evolve. Later eruptions may produce more intermediate or even felsic lavas, as the basaltic magma undergoes fractional crystallization in the magma chambers beneath the island. This is why some volcanic islands have a range of rock types, from dark basalt to lighter-colored trachyte or even faunolite. The life cycle of a volcanic island is a slow, poignant story. It begins as a submarine volcano, erupting on the ocean floor, building a mound of pillow lavas and hyaloclastite. As the mound grows, it eventually reaches the surface, and subaerial eruptions begin, building the island above sea level. The island may continue to grow for millions of years, fed by a steady supply of magma from below. But eventually, the island moves away from its magma source, carried by the motion of the tectonic plate, and the volcanic activity dies. From that point on, erosion takes over, slowly wearing the island down. Waves attack the shores, rain carves valleys. The island shrinks, sinks under its own weight, and eventually disappears beneath the waves, becoming a submerged seamount. This entire cycle, from seafloor eruption to submerged seamount, takes tens of millions of years. It is a complete life, lived at a pace that makes human timescales seem like the blink of an eye. And throughout this life, the chemistry of lava is the central actor, building the island in its youth and determining the rock types that will resist or yield to erosion in its old age. The Hawaiian island chain is perhaps the most vivid illustration of this cycle. The Big Island of Hawaii, at the southeastern end of the chain, is the youngest and most volcanically active. As you move northwest along the chain, the islands become progressively older, more eroded, and smaller. At the far end, the oldest islands have been worn down to low, flat atolls, barely above sea level. And beyond them, a long line of submerged seamounts extends across the Pacific, the graves of ancient islands that lived and died millions of years ago. And even now, a new island is forming. Loihi Seamount, located about 30 kilometers off the southeastern coast of the Big Island, is an active submarine volcano that is slowly building toward the surface. It is currently about 1,000 meters below sea level, and at its current rate of growth, it may break the surface in 10,000 to 100,000 years. It is the next in line, the newest chapter in the long, ongoing story of the Hawaiian hotspot, a story written entirely in the chemistry of basaltic lava. Let us now think about something called volcanic ash, which is related to lava but different in important ways. Volcanic ash is not ash in the sense of burned material, like the ash from a campfire. It is actually tiny fragments of volcanic rock and glass produced when magma is shattered by the force of expanding gases during an eruption. The fragments can range in size from fine dust to coarse sand, and they can be carried great distances by wind before settling to the ground. The chemistry of volcanic ash is the same as the chemistry of the magma that produced it. Basaltic eruptions produce dark, iron-rich ash. Felsic eruptions produce lighter, silica-rich ash. The ash particles are often angular and irregular, with sharp edges that reflect the violent nature of their formation. Under a microscope, they can look like tiny shards of glass, fragments of broken crystals, and pieces of pumice, all jumbled together. When volcanic ash settles on the ground, it can form thick deposits called tuff when it compacts and lithifies over time. Tuff is a fascinating rock because it preserves the texture and composition of the ash exactly as it fell. Some tuffs are welded, meaning the ash was so hot when it landed that the particles fuse together, forming a dense, hard rock that looks almost like lava. Other tuffs are loose and crumbly, preserving the individual ash particles in their original, unconsolidated state. Volcanic ash deposits are incredibly useful to geologists and archaeologists as time markers, because individual eruptions produce ash with a distinctive chemical fingerprint, and because ash can be distributed over vast areas, a single ash layer can serve as a chronological reference point across an entire region. By identifying and correlating ash layers in different locations, scientists can synchronize geological and archaeological records, establishing precise timelines for events that occurred thousands or millions of years ago. The chemistry of each ash layer is like a barcode, unique to the eruption that produced it. The concentrations of major and trace elements, the mineral assemblages, and the glass composition all combine to create a chemical signature that can be matched across thousands of kilometers. It is a remarkable application of lava chemistry, turning the products of a single volcanic event into a tool for measuring time and connecting distant places. Here is another gentle thought for the late hours. Have you ever wondered what gives some volcanic regions their distinctive smell? The answer, of course, is chemistry. Volcanic gases, particularly sulfur dioxide and hydrogen sulfide, have strong, characteristic odors. Sulfur dioxide has a sharp, acrid smell, like a struck match. Hydrogen sulfide smells like rotten eggs. In areas with active volcanic fumaroles, these smells can be quite noticeable, a constant reminder of the chemical activity happening beneath the surface. But there are also more subtle chemical effects. In some volcanic regions, the groundwater is enriched in dissolved minerals from contact with hot rock, and hot springs bubble up at the surface with a distinctive mineral smell. The water may contain dissolved silica, sulfur, iron, manganese, and other elements, each contributing its own subtle scent and color. Some hot springs are brilliantly colored, with rings of orange, green, and brown created by heat-loving microorganisms that thrive in the mineral-rich, warm water. The colors are a visible expression of the chemistry, with different temperatures and different mineral concentrations supporting different communities of life. These hot springs and fumaroles are gentle, continuous expressions of volcanic chemistry. They do not erupt or flow. They simply sit there, quietly bubbling and steaming, releasing their gases and minerals into the air and the water. They are among the most peaceful volcanic features, and they have been valued for thousands of years by human cultures around the world who have used them for bathing, healing, cooking, and spiritual practice. Let us also consider something called fractional melting, which is the complement of fractional crystallization. While fractional crystallization describes what happens when crystals form and are removed from a cooling melt, fractional melting describes what happens when a solid rock begins to melt, and the melt is extracted before the rock is completely liquefied. When a rock in the mantle begins to melt, not all of its minerals melt at the same temperature. The minerals with the lowest melting points melt first, producing a small amount of liquid with a specific composition. This first melt is typically enriched in the elements that have low melting points and that are less compatible with the remaining solid minerals, elements like sodium, potassium, and silica. If this melt is extracted, leaving behind the higher melting point minerals, the result is a liquid that is more felsic, more silica-rich than the original rock. Fractional melting is one of the key mechanisms by which the Earth generates the diversity of magma compositions that we observe at the surface. A single batch of mantle peridotite can produce a range of different magma types, depending on how much of it melts, how quickly the melt is extracted, and what conditions of pressure and temperature prevail. Small degrees of melting produce silica-rich, alkali-enriched magmas. Large degrees of melting produce more mafic, iron and magnesium-rich magmas, closer to the original mantle composition. It is a beautiful system, really. The diversity of volcanic rocks on the Earth's surface, the basalts and andesites and rhyolites and everything in between, all of it can ultimately be traced back to variations in the degree and conditions of melting in the mantle. The mantle is the source, and the chemistry of lava is the expression. Every volcanic rock is a specific answer to a specific set of conditions deep inside the Earth. Let us spend a quiet moment thinking about a phenomenon called decompression melting, which is one of the main ways that the Earth produces magma. When hot rock in the mantle rises toward the surface, the pressure decreases, and a decrease in pressure lowers the melting point of the rock, even if the temperature stays the same. This means that the rock can begin to melt simply because it is rising, without any additional heat being applied. Decompression melting is the primary mechanism that produces magma at mid-ocean ridges. As the tectonic plates pull apart, the underlying mantle rises to fill the gap, and as it rises, it begins to melt. The melt collects in small channels and veins, migrating upward through the partially molten rock until it accumulates in sufficient quantities to erupt at the surface. The entire process is driven by the simple physics of pressure and melting point, a quiet, elegant mechanism that has been producing the majority of the Earth's lava for billions of years. You can think of decompression melting as the Earth's way of breathing outward. The rising mantle is an exhalation, a slow upwelling of hot material, and the melt that it produces is the breath itself, the tangible expression of the planet's internal heat finding its way to the surface. It is a gentle, continuous process, happening right now beneath every mid-ocean ridge on the planet, producing new oceanic crust at a rate of a few centimeters per year. Silent, steady, and unceasing. And here is one more fact to carry into the deepening quiet of this night. The total volume of magma produced by the Earth each year is estimated at roughly 20 to 30 cubic kilometers. Most of this is produced at mid-ocean ridges, far from human eyes. A smaller fraction is produced at subduction zones and hotspots, and an even smaller fraction erupts on land, where we can see it and study it, 20 to 30 cubic kilometers per year. It sounds like a lot, and it is, in human terms. But, compared to the total volume of the Earth's mantle, which is about 900 billion cubic kilometers, it is a tiny fraction. The Earth produces magma at a rate that is, in proportion to its size, astonishingly modest. It is a gentle, measured output, sustained over billions of years, and it is all the Earth needs to maintain its volcanic activity, recycle its surface, and keep its chemical cycles running. The patience of it is something to marvel at, not a wild outburst, but a slow, steady trickle, year after year, eon after eon. The Earth is not in a hurry. It never has been. And that unhurried quality, that deep geological patience, is something we can borrow from, here in the quiet of the night, as we let our own thoughts slow down and our own energies settle into rest. There is a phenomenon in volcanic regions called fumarolic alteration, where the gases escaping from the ground react with the surrounding rocks, changing their chemistry and their colors. Rocks near fumaroles are often stained brilliant white, yellow, orange, or red by the deposition of sulfur, silica, and iron compounds. The original dark basalt may be transformed into a rainbow of altered minerals, soft and crumbly where it was once hard and dense. These altered zones are fascinating to geochemists because they preserve a record of the gases that pass through them, the specific minerals that form, and the patterns in which they are distributed tell scientists about the temperature, composition, and flow paths of the volcanic gases. It is another way in which lava chemistry communicates across time, leaving messages in color and mineral for anyone who knows how to read them. In places like Yellowstone, the fumarolic alteration has created landscapes of extraordinary beauty. The hot springs and geysers are surrounded by terraces of white silica sinter, deposited from the mineral-laden water as it cools. The pools themselves display vivid blues, greens, and oranges, colors created by a combination of dissolved minerals and heat-loving bacteria. It is a landscape shaped entirely by chemistry, by the slow, patient interaction of volcanic heat and surface water, creating something that looks almost like a painting. Let us think about one more aspect of volcanic chemistry that connects to our everyday lives in ways we rarely notice. Many of the metals that we use in technology, industry, and daily life were originally concentrated by volcanic and hydrothermal processes. Copper, zinc, lead, gold, silver, molybdenum, and many others are found in ore deposits that form through the circulation of hot, mineral-laden fluids associated with volcanic activity. These ore deposits form when volcanic heat drives the circulation of groundwater through the surrounding rock. The hot water dissolves metals from the rock and carries them in solution until it reaches a location where the conditions change. Perhaps the temperature drops, or the water mixes with a different fluid, or it encounters a chemical barrier. At that point, the dissolved metals precipitate out of solution, forming concentrated deposits that can be mined. The chemistry of lava and its associated fluids is, in this way, the foundation of much of our material civilization. The gold in your jewelry, the copper in your electrical wiring, the zinc in your sunscreen, all of these can trace their origins back to the chemistry of volcanic and hydrothermal systems. The elements were carried from the deep earth by magma, concentrated by the circulation of hot fluids, and deposited in the crust where we could eventually find and extract them. It is a long, slow supply chain, measured in millions of years, but it is the same chemistry we have been exploring tonight, applied to the practical business of building a civilization. There is something grounding in this thought, quite literally. The material foundations of our lives, the metals and minerals we depend on, are products of the same geological chemistry that produces lava and igneous rocks. We are more connected to the deep earth than we usually realize, and the chemistry of molten rock is part of the invisible infrastructure of our daily existence. Let us take a few more slow, wandering steps before we begin to bring everything to a close. There are a few more gentle ideas that deserve a quiet moment in the dark. Think about the concept of viscosity one more time, because it is such a central idea in lava chemistry, and it is worth letting it settle deeply into your understanding. Viscosity is simply a measure of how resistant a fluid is to flowing. Water has very low viscosity. It flows easily and quickly. Honey has higher viscosity. It flows slowly and reluctantly. And lava, depending on its chemistry, can have a viscosity that ranges from something like warm honey to something like cold tar. The viscosity of lava matters because it controls almost everything about how a volcanic eruption unfolds. Low viscosity lava flows easily and gently, spreading across the landscape in broad, thin sheets. High viscosity lava resists flowing, building up pressure in the vent and sometimes producing more forceful eruptions when that pressure is finally released. The viscosity determines the shape of the volcano, the texture of the rock, the distribution of gas bubbles, and the distance the lava travels from its source. And yet, viscosity itself is determined by just a few simple factors: the silica content, the temperature, the water content, and the crystal content of the melt. These four variables, interacting in various combinations, produce the full range of lava behaviors observed on Earth. It is an elegantly simple system, and it is a reminder that complexity in nature often arises from the interplay of just a few basic principles. As you lie here, you might notice that your own body has a kind of viscosity tonight, a heaviness in your limbs, a reluctance to move, a gentle resistance to any action more demanding than breathing. This is the viscosity of rest, of relaxation, of a body that has surrendered its tensions and its urgencies. And it is a good kind of viscosity, a healthy resistance to the pull of the waking world. Let yourself be thick and slow and heavy. Let yourself be lava cooling in the night air, gradually becoming still. Here is a thought about scale that may help you drift. The smallest structures in lava chemistry, the individual atoms and ions and silicate tetrahedra, are measured in angstroms, which are 10 billionths of a meter. The crystals that form in cooling lava are measured in micrometers to centimeters. The lava flows themselves are measured in meters to kilometers. The volcanic edifices they build are measured in kilometers. The tectonic plates they ride on are measured in thousands of kilometers. And the mantle from which they originate spans the entire depth of the planet, nearly 3,000 kilometers. From the angstrom to the planet, from the atom to the globe, lava chemistry operates seamlessly across every scale. The same silicon-oxygen bonds that hold a single tetrahedron together also determine the viscosity of a continental-scale lava flow. The same iron atoms that give a crystal its color also contribute to the density of an oceanic plate. There is no break, no discontinuity, just a smooth, continuous connection from the smallest to the largest, all governed by the same fundamental chemistry. This continuity across scales is one of the most beautiful features of geology and of science in general. It means that by understanding the behavior of atoms, we can predict the behavior of continents. By studying a single crystal, we can learn about the interior of a planet. The universe is consistent. The rules do not change as you zoom in or out. They simply express themselves differently at different scales, like a melody played in different octaves. Let us also think, for a gentle moment, about the people who study lava. Volcanologists are among the most dedicated and passionate scientists in the world. They spend their careers climbing volcanoes, collecting samples, measuring gases, and analyzing the chemistry of lava and magma. Their work takes them to some of the most remote and challenging places on Earth, from the summit craters of active volcanoes to the bottom of the ocean floor. What drives them is a deep curiosity about the Earth, a desire to understand the processes that shape our planet and to use that understanding to protect the communities that live near volcanoes. Many volcanologists are motivated by the practical goal of forecasting eruptions, and lava chemistry plays a key role in this. By monitoring the chemistry of volcanic gases and the composition of erupted lavas, scientists can detect changes in the magma system that might signal an impending eruption. For example, a change in the ratio of certain gases, like an increase in sulfur dioxide relative to carbon dioxide, can indicate that fresh, gas-rich magma is rising toward the surface. A change in the mineral composition of erupted lava can reveal that the magma chamber is being replenished by a new batch of magma. These chemical signals are subtle, but they can provide critical early warning, sometimes days or weeks before an eruption occurs. The work of volcanologists is a quiet heroism. They spend months and years gathering data, analyzing samples, and building models of volcanic systems, all in the hope of being able to give advance warning when a volcano shows signs of unrest. It is patient, careful, unglamorous work, driven by the understanding that the chemistry of lava is not just an academic curiosity, but a matter of practical importance for millions of people who live in volcanic regions around the world. And yet, there is joy in it too. Volcanologists often speak of the beauty of their subject, the awe of standing near a lava flow and watching the glowing rock move, the satisfaction of deciphering a complex chemical record in a piece of ancient stone, the wonder of understanding how the earth works at its most fundamental level. It is a science driven by love as much as by duty, and the chemistry of lava is at the heart of it. There is a mineral called plagioclase that we have mentioned several times, and it deserves one last quiet moment. Plagioclase is a feldspar, one of the most common minerals on Earth and, for that matter, on the Moon and probably on Mars as well. It forms a continuous series between two end members, albite, which is sodium-rich, and anorthite, which is calcium-rich. Any plagioclase crystal can have a composition anywhere along this spectrum, depending on the chemistry and temperature of the melt from which it formed. Plagioclase crystals often show a feature called zoning, where the composition varies from the center to the edge of the crystal. The center, which formed first at higher temperatures, tends to be more calcium-rich. The edges, which formed later as the melt cooled and changed composition, tend to be more sodium-rich. Under a microscope with polarized light, these zones appear as beautiful concentric bands of different colors, like tree rings in a crystal. These zones are a frozen record of the cooling history of the magma. Each band represents a particular moment in time, a particular temperature and melt composition, preserved forever in the crystal. By analyzing the composition of each zone, scientists can reconstruct the thermal history of the magma with remarkable detail, tracking temperature changes of just a few degrees and compositional shifts of fractions of a percent. It is a microscopic diary, written in calcium and sodium, readable only with an electron microscope and a great deal of patience. and yet the information it contains is extraordinary. A moment-by-moment record of the cooling of magma deep inside the earth, preserved in a crystal smaller than a grain of rice. As we approach the final pages of this long, quiet narration, let us simply be still for a moment. Let the ideas we have shared tonight settle around you like a soft blanket. The chemistry of lava, the elements of the earth, the crystals forming in the dark, the flows cooling under the stars, the oceans born from volcanic breath, the continents built from recycled rock, the planets beyond, each with their own volcanic story. Let us visit one more corner of the volcanic world, a place where chemistry and beauty meet in a particularly striking way. In some volcanic regions, hot, silica-rich fluids circulate through the rock and deposit opal, a mineraloid made of tiny spheres of hydrated silica packed together in regular arrays. When these spheres are arranged just right, they diffract light into brilliant flashes of color, producing the play of fire that makes precious opal one of the most valued gemstones in the world. Opal is not a crystal in the traditional sense. Its structure is amorphous, like glass, but with a hidden order at the nanoscale, an order that produces color through physics rather than chemistry. The flashes of red, green, blue, and orange that you see in a precious opal are not caused by pigments or impurities. They are caused by the diffraction of light as it passes through the regular array of silica spheres, each one only a few hundred nanometers in diameter. The spacing between the spheres determines which wavelengths of light are reinforced, and different spacings produce different colors. It is a lovely thought that the same element, silicon, that forms the backbone of every lava flow on Earth, also produces one of the most spectacular optical effects in the mineral kingdom. The chemistry is simple, just silicon, oxygen, and water. But the arrangement of these simple components at a scale too small for the eye to see creates something that has captivated human beings for thousands of years. And here, in the quiet of this night, is another thought about the relationship between lava chemistry and beauty. The volcanic landscape, when seen from a distance, has a stark, almost abstract quality. Dark lava flows against pale soil, smooth pahoho surfaces reflecting the sky, rough fields stretching to the horizon, columnar basalt rising in geometric perfection, obsidian cliffs gleaming like dark mirrors. Each of these is a landscape created entirely by chemistry, by the interaction of molten silicates with air and water and gravity. No painter designed these forms. No architect planned these structures. They emerged naturally, inevitably, from the fundamental properties of the materials involved. There is a lesson in this, perhaps, about the nature of beauty itself. Beauty does not require intention. It does not require a designer. It arises spontaneously whenever the underlying principles are allowed to express themselves freely. The hexagonal columns of basalt are beautiful because hexagons are the most efficient way to tile a contracting surface. The smooth curves of pahiho are beautiful because that is how a viscous fluid folds when its surface cools. The green of olivine is beautiful because that is how iron and magnesium interact with light in that particular crystal structure. Beauty, in the volcanic world, is simply chemistry made visible, and perhaps that is true more broadly in the spiral of a galaxy, in the branching of a river, in the symmetry of a snowflake. The universe tends toward patterns, toward order, toward forms that we find pleasing. And the chemistry of lava is one of the most vivid examples of this tendency, a reminder that the deepest truths of nature are often also the most beautiful. Let us spend one more quiet stretch thinking about the way volcanic rocks weather and transform once they are at the surface. We touched on this briefly when we discussed volcanic soils and the cycling of elements, but the process of weathering is rich enough to warrant a few more gentle moments of attention. When a lava flow first cools, it is fresh and unaltered, a pristine record of the magma that produced it. But from the moment it is exposed to the atmosphere, it begins to change. Rainwater, which is slightly acidic because it absorbs carbon dioxide from the air, seeps into cracks and pores in the rock. The water reacts with the minerals, dissolving some elements and altering others. Iron is oxidized, turning from dark to reddish brown. Olivine, which is relatively unstable at surface conditions, breaks down into clays and iron oxides. Feldspars slowly transform into kaolinite and other clay minerals, releasing silica, sodium, calcium, and potassium into the groundwater. This process, called chemical weathering, is extremely slow by human standards, but extremely effective by geological ones. Over thousands and millions of years, chemical weathering can transform a hard, crystalline basalt into a deep, soft layer of tropical soil, rich in clays and iron oxides, drained of its most soluble elements but still retaining the essential nutrients that plants need to grow. The dissolved elements that are carried away by groundwater eventually reach rivers and then the ocean, where they contribute to the chemistry of seawater. The calcium and magnesium from weathered volcanic rocks can combine with carbon dioxide dissolved in the ocean to form carbonate minerals, like the calcite in limestone and the shells of marine organisms. This process is one of the most important long-term sinks for atmospheric carbon dioxide, and it plays a critical role in regulating the Earth's climate over millions of years. So the chemistry of lava does not stop when the rock cools. It continues, slowly, through weathering and dissolution, as the rock gives back its elements to the environment. The silicon becomes clay, the iron becomes rust, the calcium becomes limestone, the potassium feeds a fern. The cycle continues, quietly, persistently, connecting the deep earth to the surface and the surface to the ocean and the ocean to the atmosphere. It is all one chemistry, one vast, interconnected system, turning and returning through geological time. And now, one last soft observation before we truly begin to wind down. The Earth is not the only planet in our solar system with active geology, but it is the only one, as far as we know, where the products of volcanic chemistry have been transformed by water and sunlight and time into the substrate for life. The volcanic soils of Earth nourish forests and grasslands. The volcanic gases of Earth became the atmosphere that shields us from radiation and moderates our temperature. The volcanic minerals of Earth provided the raw materials for the first self-replicating molecules, billions of years ago, in some warm, chemically rich pool or hydrothermal vent. Life on Earth is, in a very real sense, an extension of lava chemistry. The same elements that drift through a silicate melt: carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, iron, magnesium, are the elements that build proteins and DNA and cell membranes. The chemistry of life and the chemistry of lava share a common alphabet, written in the periodic table, and they have been in conversation with each other for as long as both have existed on this planet. This is not a coincidence. It is a consequence of the fact that life arose on a volcanic planet from volcanic materials in a volcanic environment. The chemistry of life was shaped by the chemistry of the Earth, and the chemistry of the Earth was shaped by the processes of melting, crystallization, and outgassing that we have been discussing all night. We are, in the deepest possible sense, children of the volcano, made from the same stuff, driven by the same energy, participating in the same vast, slow, patient cycle of elements. None of it requires anything from you. It is all simply there, part of the fabric of the universe, operating quietly and patiently in the background of your life. And tonight, for a few hours, you have been invited to notice it, to appreciate it, to let it accompany you into sleep. That is all. A quiet acknowledgement of the chemistry beneath your feet and above your head and in the very atoms of your body. The lava flows, the crystals grow, the earth breathes, and you rest. That is the whole story, really, distilled to its simplest form. Everything else is beautiful detail. We are nearing the end now. The topics are growing softer, the details less pressing. The chemistry of lava is vast, but we have visited enough of it to feel its texture and its warmth. We have seen the atoms and the crystals. We have watched the flows and the rocks. We have traveled to other worlds and returned. And through it all, the same gentle truth has held. Lava is simply the Earth's way of bringing its inner chemistry to the surface, one slow, glowing flow at a time. There is peace in that simplicity. There is rest in the knowledge that the Earth takes care of itself, that the cycles run without our intervention, that the chemistry of silicon and oxygen and iron and magnesium will continue to build and reshape the world long after we are gone. We are guests on this planet, brief visitors in the long story of geological time, and the lava does not mind. It flows for us and without us, with equal grace. And now, truly, we are beginning to slow down. The night has grown deep. The ideas have spread out around you like a field of quiet stars. Some are close, some are distant, some have already faded from view. And that is exactly how it should be. This has been a long, gentle journey, and every long journey has its ending. But before we reach the very last words, let us take one final, very slow walk through a few more soft images. Not new facts, but familiar ones, revisited like old friends. Imagine a river of basaltic lava, moving so slowly across a darkened landscape that you could stand beside it and watch without any worry. The surface is crusted and dark, but through the cracks, you can see the glow. Deep orange shading to amber, warm and steady. The lava moves with a kind of geological grace, unhurried, inevitable, shaped by gravity and its own chemical nature. Silicon and oxygen tetrahedra, loosely linked, sliding past each other in the heat. Iron and magnesium ions drifting through the spaces between. Tiny olivine crystals beginning to form in the slightly cooler margins. It is a portrait of chemistry in motion, painted in light and heat and stone. Now imagine the same flow. Hours later, the surface has cooled completely, forming a dark, glassy crust. Beneath the crust, the lava still moves, but it is thicker now, slower, weighted down by the crystals that are forming throughout the melt. The glow has dimmed. The flow is becoming rock, not all at once, but gradually, from the outside in, like a pond freezing from the edges. In a few days or weeks, the entire flow will be solid. The chemistry will be locked in place. The crystals will be fixed in their positions, the glass will be frozen in its disorder, and the rock will begin its long, quiet life on the surface of the earth. And that rock, in its silence and its patience, carries within it everything we have talked about tonight. The silica content that determined its viscosity, the iron that gives it its dark color, the gas bubbles that are preserved as vesicles, the magnetic alignment that records the Earth's field, the isotopes that will one day tell a scientist exactly when this flow erupted. It is all there, locked in the stone, waiting to be read. A diary of the deep earth, written in the language of atoms, sealed in rock, and left on the surface for anyone curious enough to open it. And so, as we begin to slow down and bring this journey to a close, let us take one last, quiet look at what we have explored. Not to summarize or test or review, but simply to let the most soothing images drift by one more time, like clouds reflected in a still lake. We began with the simplest idea. Lava is molten rock. It rises from the deep earth, driven by heat and buoyancy, carrying within it a rich chemistry of silicon and oxygen, of iron and magnesium, of calcium and sodium and potassium and aluminum. It is a complex liquid, full of dissolved gases and tiny crystals, and it behaves differently depending on its particular chemistry. We learn that silica is the key to viscosity. More silica means thicker lava. Less silica means thinner, more fluid lava. Dark, mafic lavas flow like slow rivers. Light, felsic lavas pile up like thick batter, and in between, the intermediate lavas have their own gentle character. We explored the textures of lava flows, the smooth, ropey surfaces of Pahoho, the rough, jagged rubble of AA, the angular blocks of more viscous flows, the rounded pillows that form on the ocean floor. Each texture a direct expression of the chemistry and the cooling conditions of the lava that produced it. We peered into the microscopic world inside the melt, where atoms and ions drift through a glowing liquid and crystals begin to form, like tiny geometric lanterns, as the temperature falls. We watched as the chaotic liquid slowly organized itself into orderly mineral structures, each crystal capturing a moment of the cooling process in its structure. We followed lava from eruption to rock, seeing how different chemistries and different cooling rates produce different igneous rocks. Basalt and gabbro from mafic magma, andesite and diorite from intermediate magma, rhyolite and granite from felsic magma. We marveled at the patience of granite, cooling for millions of years deep underground, growing crystals large enough to see and touch. We explored the hidden chemistry of volcanic gases, and how water, carbon dioxide, and sulfur behave inside the melt and escape at the surface. We learned that the color of lava comes from its chemistry, and that trace elements can paint rocks in unexpected hues. We discovered that cooled lava carries a magnetic memory of the Earth's field, locked into its iron-bearing crystals at the moment of solidification. We visited other worlds, the ancient basalt plains of the Moon, the towering volcanoes of Mars, the extraordinary eruptions of Io. We found the same basic chemistry at work everywhere: silicon and oxygen tetrahedra, melting and crystallization, the universal language of molten rock. And we connected lava chemistry to the grand story of the Earth, the building of continents, the outgassing of the atmosphere and oceans, the slow cycling of material in and out of the mantle, the creation of fertile soils and deep-sea ecosystems. The chemistry of lava is not just about rocks. It is about the planet itself, its history, its atmosphere, its oceans, its life. All of these ideas have been shared with you tonight, not as obligations but as gifts. You are free to take what resonates and leave the rest. You are free to remember or to forget. The science is there, in the rocks and the minerals and the flowing lava, whether anyone thinks about it or not. It exists quietly, permanently, like the deep heat of the earth itself. And now, as this journey comes to its end, there is truly nothing left for you to do. No more ideas to follow, no more facts to absorb, just the feeling of resting, of being still, of being held by whatever surface supports you tonight. Your breathing is easy. Your body is heavy and warm. The world outside is quiet, or if it is not quiet, the sounds are distant and unimportant. They are just the earth doing its work, as it always does, slowly, patiently, one atom at a time. Somewhere deep below you, the mantle is warm. The rock is flowing, slowly, imperceptibly, carrying heat from the core toward the surface. Magma is forming in chambers miles below the crust, dissolving gases, growing crystals, preparing for a journey that may take thousands of years. And at the surface, somewhere on the planet, lava is cooling, crystals are forming, glass is hardening, new rock is being born. None of this requires your attention. None of it needs your help. The Earth has been managing its own chemistry for 4.5 billion years, and it will continue to do so while you sleep. You can let go completely now. Let go of the facts, the names, the numbers. Let go of silicon and oxygen and iron and magnesium. Let go of silicate tetrahedra and melt inclusions and Bowen's reaction series. Let it all drift away, like ash settling on a calm lake, gently, silently, until the surface is still. You are safe. You are warm. You are resting, and the earth is turning slowly beneath you, carrying you through the night as it has carried every living thing that has ever existed on its surface. The lava flows, the crystals grow, the gases escape, the rock cools, and you sleep. Sleep now. Let the chemistry of the deep earth be a lullaby, a slow, warm, ancient song that has been playing since the beginning of the world. It does not need you to listen. It does not need you to understand. It simply is, and you simply are, and that is enough. Breathe in and breathe out. The lava glows softly in the distance, far away, behind your closed eyes. It is warm and gentle and slow. The crystals are forming, the rock is cooling, the planet is breathing, and you are resting, deeply, peacefully, completely. Good night.